My name's Gareth Funning. I am one of the lead instructors of this course, and I'm happy to welcome you all to the ICE Plus course, InSAR um, Processing and Analysis. And I will start, I think, by sharing my screen here and showing you what the syllabus is for today. Okay. So here we are. This is the syllabus document, and you all have access to it. It's linked through Moodle if you can't find it. So what we're going to have today is a series of modules, starting with material on, starting with introductions, a brief how to use Open Science Lab, and then I will give a brief lecture about geophysical modeling. Then Francisco will lead us through an exercise in actually applying some modeling. We'll have a break, and then in the afternoon, Pacific time, we'll start with a lecture on INSAR theory, and then we'll have an exercise on interferogram interpretation. So that's what you've got coming in the next 4 hours or so. So we have several of the instructors are online today. I don't know if Melissa has been able to identify them all yet, but they're all in there. But we'll start with me anyway, and we'll all of us who are on will give a brief introduction to themselves. So I'm Gareth Funning, as I said. I'm a professor at the University of California, Riverside. I mostly work on faulting and earthquakes. I have been doing INSAR for 25 years, which is quite a long time. My first interferogram that I processed on my own was of the Mani earthquake in Tibet, which occurred in 1997. So I was processing it 4 years after it happened, and that was one of the earthquakes I studied for my PhD way back when. So who else is here? I see Rowena is here, so maybe we'll start with Rowena.
I'm also of the same vintage as Gareth. I'm at Cornell University. Also worked on earthquakes with INSAR. I've since kind of moved on and I'm doing more soil moisture work with INSAR because there's just many, many things you can do with it. It's a wonderful data set.
Fantastic. Francisco has his is
Hi,
in
everybody.
darkness.
I'm Francisco Delgado. I'm assistant professor at Universidad de Chile. I have been working with INSAR for 14 years. I was a student with Matt Pritchard and Rowena Lohman at Cornell University. So, hi, Rowena. And I'm mostly a volcano geodesist. I use INSAR mostly for volcanoes, but over the years I have been trying to incorporate more research on glacier, active tectonics, and subsidence due to groundwater extraction. And my first interferogram was an interferogram of a volcano in Chilean Patagonia that had a massive ramp. That Rowena told me at the time that there was a problem with the base with the orbits of the satellite. It turned out to be that it was an ionospheric ramp. So knowledge evolves. Thank you, Rowena, for that. I always tell that story.
Who else have we got? I
Yeah.
see. Let's see. Becca.
Hi, I'm Becca. I'm a postdoc at Penn State. I've used INSAR primarily for volcanic hazards, kind of lava flow cooling, as well as magma source kind of identification and modeling. My first interferogram was a Tolica volcano in Nicaragua, and I've been using INSAR for, I think, about like 9 years now.
It is not in any particular order. I see Andrew Johnson.
Hi, I'm here a little bit in me and Simon are a little bit here in Franz's place as he's off getting eaten by bears or something. Um, um, anyway, I'm a staff scientist here at the University of Alaska Fairbanks and Alaska Satellite Facility. My main use for SAR is looking at snowmelt on land and glaciers.
And so why not have Simon as well as the other fourth representative of Franz Meyer?
Yeah, hi. My name's Simon Sweeback. I'm an assistant professor at the University of Alaska Fairbanks, and I'm interested in INSAR and how it can be used to help us understand permafrost and how it's changing.
Zach is on the call.
Hello, everyone. Zach Hoppinen, also a researcher at the University of Alaska Fairbanks, studying snow retrievals with INSAR, and my first interferogram was a car-mounted radar pair in Idaho.
Cool. Alex is on.
Hi, my name is Alex Lewandowski. I'm a software engineer at the Alaska Satellite Facility, and I'm here mainly to provide support for the class using OpenSAR Lab, which is the development sandbox that everybody will be using to complete the assignments for the course.
Okay, Rowan.
Hi, everyone. I'm a grad student working with Rowena Lohman, and I've also worked with Simon Zwiebak in the past. I've been working with INSAR for about 8 years now. And I got started at the Alaska Satellite Facility as an undergrad intern. So happy to be here. I think this is full circle because my first interferogram, I think, was Okmok as well.
We will see Ogmok in due course today. If that is all the external people, then we should move on to the EarthScope people. So Melissa is on here.
Hi, Melissa Weber. I work, as he said, at EarthScope Consortium, who's supporting the now National Geophysical Facility. Yeah. Or NGF as we call it. And I mainly handle all the logistics background information, getting you in the courses, getting you the Moodle, getting in the Slack, all that stuff. Yeah.
We'd be lost without you. There's also Austin on the call.
Well, yeah, Austin Yalakovich. I'm here for educational technology. Thank you for having me.
We'll induct you into the ways of INSAR before the end of this. Okay, so that's all the introductions. So the next thing on our itinerary or our schedule is a recap of how to use Open Science Lab, which I hope Alex will show us. Take it away.
Great. Yes. So I'm going to share a slideshow link. Hang on one second here. And then I'll share my screen. All right, so I'm sticking a link to a slideshow in the Zoom chat here that sort of walks through the process of setting up your Earth Data Login account and an Open Science Lab account and gaining access to the class lab. And now I'm going to share my screen and just sort of walk through it. Okay, so here we go. So the first thing that you'll need to do is, if you haven't already, and if you've already set up your Earth Data Login account and your Open Science Lab accounts, and you have all the access that you need, this might be a good opportunity to go grab a cup of coffee. I did give this presentation last Tuesday, so some of you probably have already gone through this entire process. But for anybody who's missed it, this is your opportunity to catch up. So. You'll need to set up an Earth Data Login account and give yourself access to ASF data, and so you can do that by heading over to earthdata.nasa.gov, users.new if you don't already have an account, and just follow the instructions to set up your Earth Data Login account, and then you'll have to take one additional step, which is to agree to the end user license agreement in order to access ASF data. And so I'm just going to hop over to my Earth Data Login account here. So after you've signed up for an account and you're on your profile page, you'll see that there are a number of menu options up at the top here, including this EULA, EULA, so that's end user license agreement. And if you haven't already done so, you'll need to, let me. There we go. You'll need to click on the Accept New EULAs link. And so when you open that up, you'll see a long list of EULAs. And actually, I've already accepted the EULA that we need, so it won't appear on my list. But I'll show you what that is in just a moment. But if you haven't accepted it, you'll identify it here and then just click the Accept EULA button. It will ask you to agree to some terms, and then you can click the Agree button. However, as I mentioned, I've already accepted mine. So I'm just going to come over here to my list of already accepted EULAs and show you what that is. And it is the Alaska Satellite Facility Data Access EULA. And so this is also all outlined in the slideshow. So if you forget the name of the EULA to accept, you can just take a look at that at the slides. All right. So that handles the Earth data login. And now you'll need to set up access to Open Science Lab. So Open Science Lab itself is a portal that allows access to multiple Jupyter Hub labs that have been purpose-built for different reasons. And there is a lab specifically built to support this the INSAR ICE Plus course. So so you can head over to opensciencelab.asf.alaska.edu and click on the Create Account button if you don't have an account yet. At that point, you'll follow the instructions to create your login or to create your account rather, and you'll be emailed a verification link. So you'll need to go to the email address that you provided and click on a link that's emailed to you. And then at that point, you'll also be required to set up multi-factor authentication. And so there are pop-ups that walk you through this process, but you'll need to set this up with an app like Google Authenticator or a similar authentication app. Once you actually have access to Open Science Lab, you'll see a number of lab cards. And if you scroll down, you'll find the 2026 technical course INSAR Processing and Analysis ICE Plus lab card, but you'll notice that it's marked restricted. So if I head over to OpenSAR Lab here, or to Open Science Lab rather. So once you've set up your MFA and you have access to Open Science Lab, you'll see all of these different lab cards. And so here you can see for the 2026 technical course, I can click the Go to Lab button, but if you haven't given yourself access to this lab yet, then you will see this restricted button instead. And so you can provide yourself access to the course lab with an access token. And so this token is it's not pasted into the slideshow because the slideshow is public. And so we didn't want the token out there in the wild. So the token is available on the class Slack channel. And hopefully, are you seeing my Slack screen? Okay, great. Yeah, so if you come to the 26 ICE technical channel, and then you head to the top and you look at the pinned, there's this little pin icon. If you hover over the pinned messages, there is this message here that has a link to the slides and also this access token, and it's this access token right here that you'll need. And so, oops. Okay. And so back in Open Science Lab, if you don't have access to the class lab yet, you'll see your username up at the top right here. So click on that, and you'll see the option to apply an access token. And so click on that, and then you can just paste that token from Slack right in here, and click the apply button. And then at that point, you'll have access to the lab, and when you scroll down, you should see that you can actually go to the lab. Now I've already started my server, but if you haven't actually started your server yet, once you've gone into the lab and clicked on the Go to Lab button, you'll see the Start My Server button, and then you'll see several different options. And so these are different servers that provide different levels of compute and memory to meet the needs of various workflows. And so there's the M6A. These names here correspond to AWS EC2 instance types. And so there's the M6A large, extra large, and then a C5 4X large. And their memory and CPU resources are listed here in the server option descriptions. So in general, unless an instructor tells you to select a larger instance type, just go with the M6A large. It's the smallest one available, and it's the cheapest to run. So unless there's a need for these larger instances, just run with the M6A large. And after you've logged in to Open Science Lab or to OpenSAR Lab, into the course lab, you will see that the instance type that you selected, let me just make this screen a little larger. You'll see that the instance type you selected is located up at the top of the screen. So if you're in a listening to a module, going through a module, and an instructor tells you to change to a certain instance type, you can see what your current instance type is here, and maybe you don't need to stop and restart your server after all. All right, and then just some general notes about working in a Jupyter Hub. So when you start up your server, you'll land on a screen that looks like this. And actually, I should delete some of these directories because when you first land here, you won't have all of these directories. So let me just get this to a state that will be similar to what you'll see upon your arrival. All right, it's taking time to delete the NISAR cookbook. But basically, when you arrive, you'll see the lost and found directory in the base environment here, and then the EarthScope InSAR environment. You won't see this ICE3 environment, and you won't see the NISAR cookbook. This EarthScope InSAR environment has been pre-built. It's baked into every server instance. And it's been set up to run all of the class workflows. So you shouldn't need to build any additional environments unless you do extra modules or you want to explore the NISAR cookbook, which has a notebook within it to build its own environment. Everything that you should need for the course is available here with this EarthScope InSAR environment. But we are missing a number of repositories, GitHub repositories, including the repo containing all of the workflows for the course. So in order to clone all of those repos to your server, just click the Update Repositories button up at the top of the screen here. And this will take about a minute, and it will clone in all of these repos. And so slowly you'll see that they begin populating here on the left. And as they start copying in, I'll show you which you'll need for the course. Okay, well, while that's thinking, I'll also just point out that that you can start a new notebook by clicking on one of these launcher buttons. So if I click on the EarthScope InSAR button, I'll end up in a brand new notebook. And as I mentioned, this carries with it all of the software that you need for the course. So I can do things like import MintPy, for example, or ICE, and those packages are available for me. Okay, and so now I see that it did get to cloning in the 2026 ICE Plus repo, and so this is where all of the coursework for this class lives. And so these are all of the different modules, and then there are some extra modules at the bottom that are not part of the course but are just sort of add-ons. And I think that about covers it. If you have any trouble signing up for your Earth Data Login account or gaining access to Open Science Lab or the ICE Plus course, please reach out on the 26 ICE technical channel. That's where we're handling all of these sorts of user support requests. You can also email us directly at UAF. Hold on one second. Let me I'll paste our support email in the chat as well. Right. Okay. All right. I'm pasting in the support email in the Zoom chat. Yeah, so please reach out if you have any difficulties at all. And unless there's anything else that I've missed, Garrett, that you'd like me to cover, I'll stop sharing now.
I think that's good.
Great.
Thanks a lot. Whilst Alex was getting ready to present, Melissa posted a few pointers about how to participate in the course during the course, and I think it's probably worth going over those at this time. That you'll see that there is a Q&A where you can ask questions. That's our preferred place for you to ask questions about the material as it's being presented. And there's also, of course, the chat, which is more for us to tell you things, I would say. So those links from Alex, for example, are a good example of things that we would like to use the chat for. If you have questions, please put them in the Q&A. We've also mentioned, of course, that there is Slack. That is the primary means of us communicating with you the rest of the time when we're not on Zoom, and the best place for you to seek help from us if you need it. I'll briefly share my screen again just to show you all that again. So yeah, this is what you should get if you log into Slack. You will have at least 2 channels. You have ICE General and ICE Technical. If you're one of the instructors, you will also have ICE instructors, but of course, that's only a few of us. So what the purposes of these channels are: ICE General, this is where you ask your questions about the material. If you have questions about the science, about the implementation, about the theory, or what to do in the exercises that we are covering, this is where you ask it. ICE Technical is reserved for technical problems, such as trying to get access to Open Science Lab and failing, or things are crashing. Please help. And we monitor these, I wouldn't say religiously, but diligently. And this is where we will be able to help you out of class time and even during class time, actually. This is the best place to ask. Of course, one of the other benefits of this is that every course participant has access to this, and so if someone else knows the answer to a question, they can also answer, and that is good. There's all sorts of literature on why peer instruction is good in science, and so yes, please help each other along if you can. Okay, so that's that. If there are any questions, please use the Q&A to ask them. And if there are not any, I will move on. And we have bought ourselves a few minutes ahead of schedule, which is almost never happens. So this is great. And I will present the next thing, which is a lecture about geophysical modeling and geodetic data. Righty, so I will share my screen again, and I will share this presentation. And I guess in theory I have access to the Q&A, but it's kind of hard to see whilst I'm talking. So hopefully someone else, maybe Rowena, will be poised to answer your questions as and when they arise. Okay, so I'm going to start with kind of a view of really the endpoint, or one of the endpoints of what we hope you'll get out of this course, which is an appreciation of how to use InSAR data to constrain models of some process. This is the vision of Paul Rosen, who was the leader of this training course for many years and is now too busy to be with us. He's the project scientist for the NISAR mission, and we had hoped to get him here to talk about NISAR, but he's had to duck out, unfortunately. So you'll have other people instead. Yes, but he always wanted us to start with like a vision of what you want to get out of the data, and so that's what hopefully this presentation will show you. Right. So when we talk about geophysical modeling, we're really talking about trying to use idealized representations of the Earth, simplified enough that we can actually compute them, to represent certain processes that occur either on the Earth's surface or in the Earth's interior. So a few examples are shown here. On the left is the earthquake cycle in a very, very idealized fashion, starting with slip on a fault being an earthquake, and then some kind of process that continues the fault to move, allow the fault to move after the earthquake, we call after slip. Some kind of process in the viscous part of the crust or the mantle that flows after an earthquake, and then perhaps some shallower process that's involved with groundwater flow that follows the earthquake as well. And all of these processes we have ways of modeling and can constrain using InSAR data. In the middle is a picture of a magmatic system with a magma chamber and feeding a dike, and the dike feeds an eruption. So there's multiple manifestations of magma movement in this model, and in theory we can also model all these and the effects they have on the surface. And on the right is something related to ice flow and ice loss. In this case, ice loss, I suppose. If you build an ice sheet during an ice house period, it imposes a load on the lithosphere, which causes it to bend, and material underneath it in the asthenosphere can flow out of the way. But if then, as is happening now on Earth, you melt the ice sheet, then you have an unbalanced lack of a load. So the lithosphere is bent, but there is no longer anything weighing it down, and material will flow back in and cause the crust and mantle to uplift. And this is happening in the very north of the northern hemisphere today, and it's an interesting phenomenon that causes vertical motions in places where you wouldn't necessarily expect them if you didn't know about this process, and is causing problems such as causing everything south of the uplift zone will actually start to subside a little, and the combination of that subsidence with sea level rise is actually suggesting that there will be problems in the decades to come in certain cities with flooding, and London is one of those, which is very close to where I grew up. Anyway, of course, we constrain these models with geodetic data, and geodetic data are data that measure the movement of the Earth's surface, at least in the context that we're talking about here. Geodesy is a much broader field than just measuring surface movement, and the people who do the other types of geodesy, those are really difficult, and I don't know how to do most of those. But that includes measuring the gravity field of the Earth, measuring the rotation of the Earth, and other things. But here we're talking about basically geodetic deformation or geodetic change, that you can measure changes in surface shape. So there are various different methods that you can use to do that. Of course, we're going to focus on the one on the left, which is InSAR, using radar to measure the changes to the Earth's surface elevation. But other types of geodetic data that you could model in similar ways include GPS, which is what's shown here. This is a map of GPS stations across the western United States, and the difference in vertical motion between a period of like normal rainfall and a period of drought. You can see that there is a dramatic change in the deformation during a drought period. And on the right is a picture of LiDAR, the differential LiDAR. So you make two LiDAR surveys of a place. This is northern Mexico in an area that had an earthquake in 2010, showing basically the difference in height of the ground between before the earthquake and after the earthquake. So you can use this to estimate the motion of the faults in that area. But we're talking about InSAR in this course, and so this is what we have, and this is a figure that I always am obliged to show in every presentation I ever give about InSAR. It's basically the essence of how it works. So here you have a satellite, a radar satellite. This is showing my age. This is one of the ERS satellites. So this was really hot stuff when I was a graduate student, although it died shortly. Its gyros failed shortly after I started. ERS-2. And ERS-2 flew at an elevation of 780 kilometers above the Earth's surface, and it illuminated the ground in the same place every 35 days. It beamed microwaves towards the ground, and it measured the echoes back at the satellite antenna, and it measured both the amplitude, which is the amount of returned radiation, and the phase of those microwaves. And if the ground were to move between one pass and the next pass over the same place, when you difference the phase from the second image from the first one, you will detect the phase change that occurred between those two passes, and that phase change is detectable in theory. So we use that difference in phase to estimate the movement of the ground. That is the whole basis of INSAR. And we use terms such as range decrease, which is to say if the range, the distance between the satellite and the ground gets shorter between the two passes, then we detect that this distance has got smaller, and we call that range decrease, and it's of course consistent with the ground uplifting or moving in on this figure to the left. Or as is shown in the diagram here, the range gets larger. The ground has moved further away from the satellite in that time, and there you would detect an increase in the distance and a positive phase change, which we would call range increase. And how do we represent the movements of the ground in INSAR? Well, we use vectors typically. So in this kind of description of the system, we have a pointing vector, which is the vector from the satellite to the ground target. This pixel down here where the arrow points is what we're considering in this particular case. And then we have a vector describing the three-dimensional movement of the ground surface. We call that U. And that could be in any direction, but depends on the process, of course. That will have maybe a diagnostic pattern of displacements. For different processes, there will be different patterns, and that's another thing, of course, that we use to interpret our data, which we will do later in today. The pointing vector, of course, is a function of the mission design to a certain degree. It's related to how high the satellite is flying in orbit, the direction that the radar is pointing, mostly those two things, and that depends on the mission particularly. The older ones had steeper instances and a narrower beam. The newer satellites had a wider beam, which has a much greater range of angles into where the radar becomes incident to the ground. But anyway, we in theory know what those are, and we use them, of course, to interpret the data that we collect. So we usually just use the unit pointing vector as the description of this pointing attribute of the radar. And of course, the purpose of using a unit vector is pretty obvious. That if you have you take the scalar product of the pointing vector with the displacement vector, so the displacement vector u, which I showed you before, the movement of the ground, and you take the dot product of that vector with the unit pointing vector, then you project the you project this u vector into the line of sight direction, and you measure basically a distance, which is related to the change in range that the satellite can detect. So you're taking the component of motion that's in the pointing vector direction, and that's what you can identify with INSAR. And so yes, we will show you in many cases interferograms that have range change in them, and we use that then to try and understand the process that happened to the ground. And the trigonometry is on the right if you care to look at it. I will say at this point that there is a caveat that is important, and that people don't necessarily all use the same sign convention in INSAR, including me at various times. So I'm part of the problem here. Depending how you define your pointing vector, you can get a different answer. You can define the pointing vector from the ground to the satellite instead of from the satellite to the ground, and then your interferogram will not be in range change. It will be in some other measure, which I typically call ground line of sight displacement or ground displacement. But obviously that will have the reverse sign to where you point the satellite. The satellite's pointing, the radar's pointing to the ground rather than the ground's pointing to the satellite. So yeah, you should be careful to interpret any data you see based on which sign convention is used. And if people are responsible users of INSAR, you should tell people what the sign convention is preferably in the figure caption or something like that of a diagram showing an interferogram. I try very hard to do that these days because I understand that this is a problem. Of course, if you have some understanding of the process you're looking at, then you should be able to tell which way round which convention is being used. But sometimes that's not the case. I in one of my papers from my postdoc, I was looking at an area of Northern California that had some prominent aquifers in it, and I wasn't really making a big deal about those. But you know, you could see that they were very clearly subsiding in the data set I was looking at. They were moving down. But in the next decade, when I processed the next data set, they were moving upwards. And it took me a very long time to figure out that's what's going on. That you know, that actually it was a different regime. They were pumping less groundwater in that decade than they were in the previous one, and so I had to think very hard and look at other things and double check the sign conventions and everything before I came to the conclusion that actually now the ground was rising in places where it had previously been subsiding. Okay, as you'll see, when we form interferograms, you difference two phases. You difference the phase of the first image, which we call the reference, from the second image, which we call the secondary. And depending on which of those two dates is the oldest, if the reference date is younger than the secondary, then your interferogram should be in range change convention. And if the reference date is the younger of the two, then it will be in ground displacement. And we will see later on. Okay, so what do you do with this? Well, once you've made your interferogram, of course, the next thing to do is to try and figure out if you can match the pattern of displacement that your interferogram shows with a model. And so, for example, if we're looking at an earthquake, you could make a model somewhat like this. This is a synthetic interferogram trying to represent an earthquake. And there are a bunch of geological parameters that you could estimate, each of which, if you change them, will change the pattern. So here it's strike, dip, and rake. If you know what those terms mean, that's great. Strike is the orientation of the fault on the map. Dip is the angle that it's inclined to the horizontal, and the rake is the direction that the fault actually moved. And this combination of parameters gives you this pattern here, which is a normal faulting earthquake. More formally, you could write that as the model displacements are some function of a bunch of model parameters. You would also have things like the depth and the location of the fault included in those parameters. And then there's another form of modeling that if we call this is a forward model, I should have said. So here, basically, we are taking a bunch of assumed numbers and plugging them into some theory that will give you this model displacement. On the other hand, if all you start with is model data, is measured data, in theory, you are also able to take that and solve for the model parameters that give you this pattern. So this, in this case, becomes an inverse model, where now you know the data and you infer the model, whereas in the forward model, you know the model and you calculate something like the data. And so, of course, in inverse modeling, what you're trying to do is to match the pattern based on the set of model parameters that you solve for. So in this particular case, which is an earthquake that we will be looking at later on, here is the measured displacements. Here is a model that purports to fit those displacements, and this here is what we call the residual, which is the difference between the data and the model. And so here, these are all on the same scale. You've accounted for most of the signal by the time you get to this point. So this is a reasonably good fit to the data. It's not perfect, and that the imperfections of the fit come more or less from the simplicity of the model I'm using. I'm using a single fault with only one rectangle to represent the earthquake, and it does a pretty good job considering it's that simple. When it comes to actually the theory underpinning a lot of these models, one of the most important things that's involved in the treatment that we use is that the crust behaves like an elastic solid, and this idea has been present in earth science since the early 20th century. One of the most famous papers on earthquake science is this paper from the Lawson report into the 1906 earthquake by Harry Fielding Reid, who realized that if you looked at the displacements along a line of triangulation stations from before the earthquake and compared them to the displacements differences measured during the earthquake or spanning the earthquake, the ground was moving in one direction before the earthquake, and then it moved in quite a different way after the earthquake. And if you sum those two sets of displacements, you actually estimate a block offset along the San Andreas fault. So there was a loading phase where you're bending the crust, which is sort of in this diagram approximated by a straight line. We know it's not quite a straight line; it's actually an arctangent function. And then in the earthquake, you can see that this line A to B is moving in such a way that if you sum this line with this one, you get something like a step in the fault. So over one earthquake cycle, the fault moves along in a step. Anyway, that's probably more detail than you need from me right now. But knowing that something is elastic, then we can model it. And typically, the simplest setup that we can use to model elastic displacements is an elastic half space, which is a theoretical construct where you can imagine like a cube or half of a cube, where everything above, there's some interface that's infinite in extent, and above it you have like nothing, like have air or vacuum, and beneath it you have an elastic solid, which has isotropic properties. It doesn't have any particular strength variation in any particular direction. It is uniform. And this is the simplest elastic model that's realistic, that includes the Earth's surface that we have. And of course, all of our geodetic measurements are made on the surface, so we do need the surface to be included in this model. And then within that elastic solid, we have some structures. So here, for example, is a fault represented as something embedded in this half space, but you could also have different geometries for magmatic bodies and things like that. So yeah, we have a number of classic models that have been developed to try and explain elastic deformation of things in the Earth's interior. So the simplest of all of them is called the Mogi source, or the Mogi model. This is a spherical body embedded within a half space, where if you have a change in volume or a change in pressure, and there are treatments of both of those, you can calculate what the resulting change in surface deformation is. It's extremely simple. You can see it's an analytical equation, or there are two equations, one for horizontal displacements and one for vertical displacements. And it's radial in that, the horizontal displacements are the same in all directions, which makes it simpler to calculate. And yeah, you just need to know a handful of things. You need to know the depth of the source. You need to know the change in pressure or the change in volume, and you need to know the dimensions of it, and off you go, and you can calculate the surface displacement field from that. And because it's analytical, because you just need to plug in numbers into an equation, it's extremely fast. So this makes it very, very, very beloved of people who want to try a lot of different geometries, a lot of different source locations, a lot of different depths, to try and solve for the displacement field. And the first exercise we will do with you, it will be using a Mogi source model to try and explain deformation of a volcano. That's Francisco in a few minutes' time. If you're looking at things that are a little bit more complicated, maybe like faults or even rectangular dikes or sills, the next sort of most complicated model is called the Okada model, and that is a rectangular dislocation embedded in an elastic half space. And this allows you to model slip on the surface, so as in the expected deformation in an earthquake, or opening and closing of that along that surface, which is what you would use to model a opening dike or a collapsing dike or sill. So this is still an analytical model. It's a much more complicated one. I'm told that Okada gets all the plaudits for this solution that he published in 1985 because he was the first person to try and integrate these complicated equations without making any mistakes. So here's the first clean analytical solution of the elastic equations, and we still use the subroutine that he produced to calculate surface displacements today. And I think tomorrow I will show you an implementation of that in a Jupyter notebook. So this is still really fast to compute. It's great, and you can model more than just one type of process with it, which is great. Also, however, it still may be a little bit simplistic in that if things aren't perfect rectangles, then you're not going to fit the data perfectly, and that was the problem with the earthquake I showed you before. And people also find it's difficult to build more complicated models out of rectangles. They don't tessellate together particularly neatly. So that's an issue that some people have when you try and make more complicated models. If you want to go to the other end in terms of complexity, so I showed you Mogi and Okada, and those are both very simple models. Of course, you can make a model as complicated as you want if you have the computational resources to do so. So for example, here is shown a finite element mesh of the Himalayas, the sub-Himalayas in Nepal, where there was an earthquake in 2015, a pretty large one, and with some colleagues in the University of Memphis, I tried to model this earthquake using a finite element model. So there are 7 million tetrahedral elements defining this volume of material here, and the fault is in there, and there's realistic topography in here, going down from the Ganges Plain, which is close to sea level, and the mesh included Mount Everest, which was the highest point on the surface. And you can embed in this also different material properties if you know them and want to, and different strengths. You can include different deformation mechanisms. So along with pure elastic motion, you could also model viscoelasticity, which is important if you want to understand sort of the response of the earthquake in the lower crust and upper mantle. But anyway, this is just to say you can make your model as complicated as you like. We know how to do this, but very few people go to this trouble usually because it's a lot of work. Making the meshes complicated, and computing the displacements from such a model is also quite computationally expensive. But in some cases, this might be the thing you want to do. And in between, just to show, you can learn a lot from looking. You can take slices through your model and understand how displacement varies as a function of depth, which I don't think anyone does normally. That's a really interesting feature of this model. And then in between, in complexity between, say, the Okada model and the finite element model, there are models that we call boundary element models, which try to understand surfaces. You can understand the Earth's surface, and then the structures that you try to model in the Earth's interior could also be surfaces, and you can build these out of tessellated triangles, which might make it easier to do. So you can make more complicated shapes if you have a bunch of triangles building up your mesh. And that certainly can be the case for faults or other types of fracture or dikes, or in this case this is a hydraulic fracture. You can also make cavities out of shapes if you want to, although that tends to be a little bit unstable in the particular code I'm showing you, which is called Poly3D, which is one of the original triangular element codes. But there are several different ones of this type out there now, and this forms a happy medium between wanting more complexity and it not taking forever to run. So these models are maybe of interest. They're faster than finite element models. They can allow you to have these complicated source geometries, and you can also do things like calculate stresses from those. Whoops. But these are still quite simple in that they don't allow you to have changing material properties, and they still can be quite slow, although they are not as slow as they used to be. People have realized some pretty neat mathematical tricks to speed up the computation of these. And a lot of the models I run now are of this type. So if you want to be me, maybe one day you might want to move to using boundary element models. Okay, so that's what you could use to try and reproduce your pattern, but there are a few more practicalities to mention. One is that the number of, if you're using interferograms, so InSAR data, you are going to generate images that contain millions of pixels, each of which is a measurement of displacement or an estimate, because sometimes those estimates are corrupted by things like atmospheric noise. We will talk about that later in this week too. But you don't necessarily need every single pixel or the information of every single pixel to reproduce an earthquake. What's shown here is an interferogram of an earthquake which has been downsampled, which is to say I have averaged certain areas into larger pixels, larger blocks. And that's because if you're a long way away from, the fault for this earthquake is where the color change is, right down here. And these are measurements of distance in, I think, I can't read all. I can't see all the axis and annotations, but these are thousands of meters away. This is something like 100 kilometers away from the fault up here. And so 100 kilometers away, all the pixels are going to move about the same distance. They're not really going to change very much, at least not due to the movement of the fault down here. So you're far away from the earthquake, and this is effectively zero displacement over here. So we can treat this whole area as one pixel with a very small displacement. And it only really matters until you get once you get quite close, what things start changing down here, and you might need to use smaller blocks to describe the displacements in these places, because they're changing laterally so abruptly. So yeah, you can reproduce the near fault displacements with small blocks, and then the far field displacements with large ones, and you turn what used to be an image that contains several million pixels into an image that contains effectively several hundred blocks. And you don't lose really any information in doing so, because most of this information is redundant. It doesn't really tell you anything new. So yeah, we like to downsample our data. So once you have a few hundred data points instead of a few million, computation of the displacement of each one of these is much faster than it would be if you're trying to calculate the whole interferogram. And this allows you to use several modeling tricks essentially to solve for even quite complicated models in an efficient manner. So that's one thing. Another thing is there are differences between the types of inverse modeling that you do. Some models are linear and some are nonlinear, and it makes a big difference in terms of how much computation time it takes to run them. So a linear model is one in which there is a linear relationship between a parameter and the modeled displacement field. So that parameter for earthquakes would be the slip of the fault. If you fix the geometry of the fault, so you're looking at exactly the same fault every single time, and all you vary is the slip. If you double the slip, you will double the displacement of the model. So you see here, this is a model of an earthquake with 0.5 meter of slip, and then if you double the slip, then you get a larger displacement, but the displacement is in the same place. This little shape here is the same place as this one, and if you double it again, then again all you do is double the amount of displacement. So this pattern looks more complicated. That's because in the original one, the contour interval is not sufficient to capture all the complexities of the deformation field. The displacements were small. This would be the same shape as you would get for this, but with larger slip. And the advantage of this is that basically, if you do fix the fault geometry, then it's a very quick process to go from the measured displacements and estimate the amount of slip. You use what we call standard least squares methods to do that, and it's a very quick calculation. So going from because there's a linear relationship, you can use slip to estimate displacement or displacement to estimate slip, and either of them is quick and easy to do. Unfortunately, many models are not linear. If you want to model something like an earthquake and you don't know a priori what the fault geometry is, then you have to solve for all those things, like the length of the fault, the depth of the fault, the dip of the fault, and the orientation of the fault. All those things, and the position also. All those things are nonlinear parameters, which is to say they don't have a simple relationship. You can't double, say, the depth and get double the displacement. That's not how it works. In fact, I'm showing you here what happens if you change the depth of the center of the fault. So this is the same picture I showed you before, 2 meters of slip on that same fault geometry. But if you push that fault deeper, then a few things happen. One, the displacements get smaller, because the fault is further away from the surface now. It's going to have less of an effect on the surface. But you also see that the areas where the displacement is happening have moved further away from the fault. No longer do you have this very, very sharp discontinuity right at the fault. Now there's a sort of a gentle variation on the surface. Yes, you have negative displacement and positive displacement, but now they're not sharp. They're not like right next to each other. If you push it even deeper, then the pattern gets even more washed out. These blobs move further away from this line, which is where the fault would be, and they get even smaller in displacement. And that you could reproduce this kind of thing with many other of the parameters. You wouldn't get the same patterns sort of changing, but you would get similarly non-linear effects that are difficult to capture easily with simple tweaks to the model. So in that case, what you have to do instead of the simple least squares inversion that you do for a linear model, you have to use something like an optimization approach, which means that you take your fault model and its parameters. For a single Akada dislocation, for example, there would be 9 parameters describing where that fault is and how it moved. And you would use an algorithm to play with those parameters and see what it does to the fit to the data. If it makes a change that improves the fit, it will keep trying to change that parameter until the fit doesn't improve anymore. Then it would try to vary a different one. So it would maybe start with the strike. The strike is the angle that the fault takes on the map, the orientation on the map. So it might change the strike until it hits about a location which it likes. It might change the location next. It might change the dip next. It might change the depth after that. And eventually it will sort of home in on a model which fits the data well. But it would require you to calculate the model thousands and thousands of times to do this. So if your model is slow to run, this is going to take a very long time. And that is really the problem with these sorts of nonlinear models. But if your computer is big and strong enough, then maybe you can still get a result that you like using these methods. You just have to be careful. I think that is all I've got. And I think also, miraculously, I'm actually finished on time. It might be a first in the generation of this course. Thank you, everyone. If there are any questions that haven't been answered, or if there are questions that anyone would like to raise again, I see people have been answering them diligently while I've not been paying attention. Is there anything that came up that someone would like to ask, or? I'm going to take that as a no. In which case, we will move on to the first practical exercise with Francisco, when we will actually do some of this stuff. Actually, do you have a question you wanted to ask right now?
Yes, may I?
Of course.
Yeah, so thank you for this wonderful presentation. So my question is, like, you showed that how LOS is different than the range parameter, right? It's the difference how the author presented with the arrow. So if I'm working with an area which is showing a deformation which is towards the satellite, so that is known as LOS, or that's towards the range difference?
That would be range decrease, or in the range change convention. And if you're using and that would be a negative signal,
Yeah,
if
that's
you're because the distance to the ground got shorter. But if you're in the other convention where the pointing vector is towards the satellite, that would be a positive signal in the case that you're in that sign convention. And that's the issue with there being two sign conventions. That a positive signal in one is a negative signal in the other, and you need to be very definite and clear about which of those two sign conventions you're using. Otherwise, people will get confused.
okay. Thank you.
Thanks. I'm going to hand over to Francisco for some practical insight.
Okay, hi everybody, can you see my screen? Yes, no? I think yes.
Yes. Well, is it supposed to be a slides or?
No, the Jupyter Lab, the OpenSAR Lab
Okay. Yep.
interface. Okay.
We can see
Okay,
it.
great. Okay, great. So as Garrett said, I'm going to guide you all through an example of modeling an interferogram with a simple MOGI source model. So we have to go to the OpenSAR Lab interface. We have to click here on 2026 ICE Plus, double click. So we'll just show up the different examples of the different activities that we have for the course. And we have to go to 1.2 geophysical modeling with InSAR. And in here, we need to open the Jupyter Notebook Airscope InSAR geophysical model. Double click and it will launch. Okay, so this is an example made by Franz Meyer at the University of Alaska. He couldn't be here for this module, so he asked me to teach this part of the InSAR course. So what we're going to do in here is just to use a simple MOGI model to describe how it can explain InSAR data that gets acquired over volcanoes, how we can do a simple grid search, which is like the simplest way of performing a pseudo inversion for the best fit model parameters of the MOGI source model, and how we, under certain assumptions, how are we going to retrieve those source model parameters. So after I will guide you through all this tutorial, this notebook at the end includes free homework assignments that you need to answer on the Moodle platform. So first thing that we need to do for like every Python course is just to import several libraries that are used for running this example. So these libraries are mostly NumPy for mathematical calculations and Matplotlib for performing all the plotting that we are going to use. The rest, like OS, copy, and subprocess, is just to move around files, copy files, and things like that. So we click in here and we click on the play button, and it will move as it performs the operations. So the test site that we are going to work with is Okmok volcano in Alaska. Why this particular volcano? Because Okmok is one of the best examples on Earth where INSAR records an outstanding ground deformation signal related due to changes in the pressure of the plumbing system. And this is a volcano that is known to deform since the formation was discovered in there almost 30 years ago by Shonglu. So there is a very long, dense record of ground deformation spanning back to 1992, I think, with all ERS data, and the volcano continues to deform since then. This has been observed by all sorts of INSAR missions, from the old ERS to the newest. I don't know if NISAR yet. I don't know if it has acquired relevant data in this particular area. But for example, Sentinel can record excellent ground deformation data in here. And the deformation has also been observed by dense campaign and continuous GNSS networks. So in addition to being one of the best examples of ground deformation data, the advantage of the deformation signal is that it can be explained by the simplest a source model for a pressure source located in a volcano, and that is the Mogi source model. And that is the Mogi source model. So for this example, we are going to model an interferogram calculated using two SAR images from the ERS-2 satellite, and these were acquired in August 2000 and July 2002. So it is an interferogram that spans almost 2 years. Because we are in Alaska, Alaska has seasonal snow, so INSAR most likely doesn't, except maybe for NISAR, it doesn't really work in the winter, so we have to rely on making the observations in this particular region in the summer. But when you work with summer interferograms, so from let's say mid-June until mid-October, the coherence, which is a measurement of the quality of the pixels and in most detail of how similar are the backscattering properties of the ground surface, the coherence is very high when you work with summer images. So this is an interferogram that spans 2 years, and during that time span, it recorded around a little more than 3 centimeters of ground deformation recorded by INSAR. So, and in the right, what we do observe is that there are several GNSS vectors when there was only GPS. This is data recorded a long time ago. And it shows that the horizontal and the vertical components also show that there is a pressure source that is pressurizing, and that results in extension in the horizontal components and uplift in the vertical components of the GNSS data. So the goal of the problem of this particular notebook is to estimate the values for the 4 unknown model parameters that describe a pressure source. And these 4 unknown model parameters, as Garrett said, are the source location, X, Y, and Z, horizontal location and the depth of the source model, and the source volume change. It is the simplest model, or one of the simplest that exists for modeling INSAR data. The screw dislocation, the 1D screw dislocation model for a log strike slip fault is simpler, but that is beyond the scope of this particular notebook. So, after having said all that, what we're going to do is to get some. So we need to, before running, we have to check that we need to clear all the output of all cells, because I was running this a while ago. So we need to clear the output of all cells, and we will run it again. So click on here to import the libraries, and click until we start moving to the blocks that have code. So here it will display the first command, create and move to a directory that has our files. So it displays the current working directory. Second, we will have to download the interferogram that is already processed. This is an old ERS 2-year long pair. The data is old, but it doesn't mean that it's useless. It's actually very useful. The original SAR data are stored at the EarthScope repository, so you can download it and process it on your own. For example, using the old ISCE software, or even if you can get access to the old ROIPAC software from like 15 or 20 years ago, you can also process this old data with using those software. So we'll get, by clicking in here, play, we will download the data, and it's already downloaded. So the file name, it states E451. It accounts for ERS2. 451 is the track number, and the other 2 numbers and the year, month, day of the SAR images that were acquired, that were used to process the interferogram. The UNW extension means that the interferogram is unwrapped. So the phase that varies between -pi and pi has been converted to a continuous distribution using a phase unwrapping algorithm, and that is something that will be explained in more detail during the INSAR theory modules of this course. Next, we have to define some variables, which are the sample and the line the number of samples and the number of lines, which is the number which are essentially the dimensions of the interferogram. Every the interferogram is geocoded every 40 meters, so we have to define the posting, and we will define half the radar wavelength. ERS, Sentinel, MBSAT, and other missions like RadarSat-1, RadarSat-2, RadarSat Constellation mission are C-band missions. That means that they have a radar wavelength that is approximately 5.5 centimeters. The radar wavelengths are not exactly the same. For ERS, if it is 5.6 centimeters. For Sentinel, it is 5.55 centimeters. So here we will make it simple and we will just work with half the radar wavelength, which is 28.3 millimeters. Here we will work with millimeters as units of distance. So now we will read the interferogram. This just checks that we have an interferogram, that we are loading a data. And then in the next line, we will replace, we replace all the nans with zeros, all the elements that have no value with a number 0. And we will also multiply our interferogram by half the radar wavelength divided by 2 pi. This, what it does, it converts the phase into a unit of ground deformation. And the factor to convert is the radar wavelength divided by 4 pi. So every radar wavelength, you have a 2 pi phase cycle, and you also need to account for a number 2 factor because the radar signal is traveling back and forth. It's traveling from the satellite to the ground surface and then back to the satellite, so it needs to be halved. So we convert this to ground deformation units by multiplying by this factor. Every time that you work with a new satellite, with a different satellite, you need to know what the radar wavelength is, and that information is well known and available in many different sources. So we click on that, we replace all the nans with zeros, and now we will mask the data to remove all the nans with zeros. So in the next block, this is just loading the data and masking for the different things. So we need to calculate the bounding box because we need to work with coordinates, because the MOGI model, it's done to be calculated using rectangular coordinates, Cartesian coordinates, UTM coordinates. So that is what the next block chunk of code does. And then we will create a directory to store the data that we are going to plot. And that is homework 1 data plots, where we will store this. Then we will click on the next chunk of code, and this is just a function to plot the data using the simple matplotlib library. One key line is here where it says imgrab. This line just takes the already ungrabbed interferogram and it will forwardly grab only for visualization, because under certain situation it is simpler to observe the data grab. And in this case, it will help us to compare how an ungrab versus a grab interferogram looks like. The rest are just plotting options where the key lines are ax1 imshow. Imshow is the function that takes the infile or the infile, which is the ungrab phase, and the ungrab phase for visualization. And then we will plot the data. This will take a few seconds with our interferogram. So far, the only thing that we've done is just read a file that it is in a binary file format. All the InSAR data are stored with specific file formats that are not necessarily the same that are work for other geospatial data. They are not, let's say, like GOT files. They come in their own file formats. We call it, for those of us who work with the JPL software, from ROIPAC, ICE, ICE2, ICE3. It is called the RNG file format, and those are just real 1 or 2 band real number files. So all this code essentially just reads the data and make this nice plot. So what we're observing here is just the 2-year-long interferogram. On the first panel, we do observe the ungrab phase, and in the right panel, we observe the grab phase. So they look essentially the same, except that for the grab phase, we took the already ungrabbed interferogram and we regrab it to make it easier to visualize. So if we count the number of cycles, for example, take one value here and then go from this tone of yellow, from this tone of, let's say, green to this other tone of green, we already counted one phase cycle, and that means that the distance between the radar and the ground surface has changed by half by one phase cycle or half the radar wavelength. And by counting the number of cycles, we know the amount of ground deformation. In the INSAR community, even regardless if we study earthquakes, volcanoes, aquifers, glaciers, and so on, and as Garrett said, we are still not having an agreement on the best way to plot INSAR data. And that is unfortunate because everybody uses their own convention, and that can be quite confusing for people who are not used at looking at this data. For example, some people, especially from space agencies, like to present the data as plot as distance, range change, distance between the satellite and the ground surface. But for many earth scientists, that is not really useful at all. So you should check in every paper that you see whether they are displaying the ground surface observed by the sat in the line of sight direction. The line of sight is the vector that contains the orientation that tells us the pointing direction from the radar antenna to the ground surface, or if we are looking at the range change, which is the change of distance between the satellite and the ground surface. Essentially, one is the negative of the other, so you can multiply them by a factor of -1, but you should always check because, as Garrett said, it can be confusing, quite confusing if you are not really used to working yet with this type of data. But it's just a factor of -1. So what the map on the left shows is the ungrabbed interferogram. This color scale is saturated between -30 and 30 millimeters, so we can change it. Can we change it? For example, we can change it in here by, let's say we can put it to -6, -60, and 60 millimeters, and we will plot it again. So it will take a while, I think. Is it changing? Oh yeah, it's doing something, yes. And now the color scale changed. So now our color scale is saturated between -60 and 60 millimeters. How you plot this is arbitrary. It depends on what you want to show. So we can make it slightly less saturated. We can plot it between -100 and 100 millimeters. That's plus minus 10 centimeters. Let's do it again. And it will take a few seconds. And yes, and now it looks probably slightly better in my opinion because it is less saturated. It is not saturated with respect to the maximum value. By doing this, the background non-deforming region is observed with an average value of 0. But if you want to really show how the background deformation looks like, it's better to display the data with a smaller dynamic range, for example, plus minus 20 millimeters. Again, this is arbitrary. It depends on what you want to show. Yes, and here it's very saturated with respect to the ground deformation signal, but by changing the color scale, we're starting to see that in the non-deforming regions outside of this massive blue eyeball pattern, we do observe some tones that are yellowish, that are light blue, that are green, that are slightly orange, and they can be considered as noise for what we're trying to do. In INSAR, we're not working with white noise, we're working with spatially correlated noise that arises from a variety of factors, including delays by changes in the troposphere, let's say by changes in the water content, by changes in the atmospheric pressure, by changes in the ionosphere, and so on. And there will be a specific class on this topic later on. So for simplicity, let's go back to the original color scale, plus minus 30 centimeters. What is clear from the example is that the ground deformation signal looks like kind of circular. And that is a strong indication from a qualitative point of view that this signal can be explained by essentially a pressure source that is kind of symmetrical. And that's why we use the MOGI model. So what is the MOGI model? The MOGI model is just the ground displacement in 3D due to an inflation source located at a given location with a volume change. So take the locations of the source XS, YS, CS, take the observation points X, Y, Z, and then calculate the simple formula that will give us the ground displacement. The term at the bottom here, R, is just the horizontal distance between the source and a given observation point. So this model, it's a simplification. It is a simplification of the structure of a volcano. No one is telling us that that we actually have a spherical pressure source beneath a volcano. We use it because it's fast, as Gareth says. This runs in just a few seconds, or sometimes in less than a second, when your computer is quite powerful. And we use it because it works to explain ground deformation data. We know it's biased, we know it's a simplification, it's an analytical approximation from the problem on linear elasticity on solid mechanics, where you take a spherical cavity subject to the boundary condition that there is a normal stress on the cavity wall, and that will result in ground deformation that can be measured using InSAR or other satellite geodetic data. Essentially, we use it because it works and because it is simple, not because it is realistic. Because we know from advance that we don't really have spheres full of molten material beneath a volcano. But surprisingly, this model works quite well for modeling data, and also it works quite well for providing insights that are quite useful, like the location, the vertical location of the pressure source and the volume change. And that is information that can be easily compared with, for example, inferences from petrology on the storage depth of magmas, or from the volume changes that result when you have an eruption. And if you are able to measure the amount of extruded volume during, let's say, an explosive eruption. It depends on the Poisson ratio, and in this particular calculation, we will use a fixed value of 0.25 because it is realistic of multiple varieties of multiple types of rocks in the upper crust. So these equations, which are quite simple, you can code them in just a few lines of your favorite MATLAB or Python code. You can code them in a few lines. It produces the east, north, and vertical ground deformation. But with INSAR, we are measuring ground deformation along the radar line of sight. As a simplification, for volcanoes where you have pressure sources like this, where the ground deformation pattern looks like kind of circular, we know that the deformation is dominated by the vertical component that it is projected along the radar line of sight. So for volcanoes, we make the assumption, the simplification, and we call the change in distance between the satellite and the ground surface as either uplift or subsidence. But keep in mind that but when working with INSAR, you should always take into account that this is along the radar line of sight. This is not pure vertical deformation. It is deformation that is mostly dominated by the vertical component along the radar line of sight. And that is just calculated by taking the dot product between the 3D surface displacement vector, like the one accounted for, like the one that you can calculate with a MOGI source, and the look vector, which is given by the orientation of the radar antenna and by the satellite heading direction. So this is, here the satellite is flying into the page, it's looking down to the right, and on the left what we see is how the satellite is flying. This is a satellite that is flying mostly in a polar orbit. That means that the orbits are more or less from north to south or from south to north, and the line of sight vector is pointing in the right direction. Unless explicitly noted, all the civilian SAR missions that you use for INSAR, ERS, ENVISAT, Sentinel, ALOS, ALOS-2, Cosmos Skymet, TerraSAR-X, RadarSat 1 to Constellation, etc., all of them are right-looking, except, for example, NISAR. NISAR is left-looking, and some satellites have the capability to observe on the right and on the left. But in general, unless explicitly stated, all the SAR missions are designed to work with a right-looking radar. So we have to take the 3D ground deformation vector and multiply it by the line of sight vector, and that is just done by a simple dot product between the UX, UY, and UC, which are the components of the ground deformation predicted by the model, and LX, LY, and LC, which is the line of sight vector. And this vector depends on the L angle, which is called the look angle. It is the orientation of the radar beam with respect to the vertical. and T, which is the heading angle. And there are many conventions for the heading angle. And in this particular notebook, we will use it as defined positive clockwise with respect to the north axis. Other software, some software have a relatively weird convention, but this is something that you should always take a look. So the relevant angles in here are L, the look vector, and T, the satellite heading vector. So the code, what it does, we will take a position X, S, Y, S, C, S, and B for the volume change. We will calculate the ground displacement at any given point. And then we will project the ground deformation along the satellite radar line of sight to calculate the displacement that is measured by InSAR. And by using the definition of an inverse problem with G, the formula that contains all the relevant information, which in this case is this formula for U, M, which are the 4 model parameters, one linear, which is the volume change. The volume change is linear with respect to the other parameters. So if you double the volume, you get double the ground deformation. But if you, for example, double the source depth, you are not getting exactly double the ground deformation because the horizontal position and the source depth are non-linear parameters. The MOGI model is actually, in my opinion, an excellent toy example for any inverse theory class. I think it's far more useful than learning tomography for learning inverse theory because it's mathematically simple, it is non-linear, but it's also very useful and easy to calculate and easy to visualize, and many people use it around. So the next chunk of code, what it does, it calculates a forward model for a MOGI source, N1, E1, and the depth are the easting, the northing, the easting, and the depth location. Delta volume is the source volume change. Northing, easting are the coordinates on the points on the horizontal plane where you are calculating the ground deformation. And P-look is the line of sight vector. So this function just takes the previous formulas and in a simple way calculates them. So in the next chunk of code, we need to take into account the heading direction, which is -13 in this case, and the look angle, which is 23. 23 is a famous number for a look angle because that was the look angle for the only beam of ERS, and it was also the look angle for the IM2 beam of the old MVSAT satellite that, for us who have been using InSAR for a while, we work with MVSAT data for 10 years or even more. And here in PLOOK, we just take the previous formula for the line of sight for the look vector and calculate it using these angles that we are providing. Next, we define the northing and the easting components. And finally, we calculate the forward MOGI model and the forward MOGI, the forward MOGI model. And one thing that I forgot to mention, here in the code we provide the X, Y, Z location of the source, the volume change, the easting and the northing and easting component, the P-look vector, and in the previous code, P-look is used to calculate the dot product between the 3D displacement and with that vector to get the change in distance along the radar line of sight. So click on play. And in the next chunk, we will plot the output of the forward MOGI model. Here, we will use a fixed depth of 2.58 kilometers and a source volume change of 0.0034 cubic kilometers. This is 3.4 million cubic meters. We will then vary the easting and northing parameters to demonstrate how the model predictions vary when we change these parameters. So we do that. And let's see what happens with the code. It will take a few seconds. And here we are. Yes, here we are. So in this code, CS TS is the source volume, is the source depth in kilometers. The volume is in cubic kilometers, the volume change, and we are plotting, and we are defining, and here we are plotting for different source for 9 combinations of source locations, which are spaced every 13 and every 12 kilometers. So the output that it generates is a 3x3 panel, where we just in the first row we vary the northing location of the MOGI model. So just by increasing the northing component, for example 16 to 21, we are essentially shifting the location of the source to the north, as simple as that. At the middle column, we are doing exactly the same, but in here we horizontally shifted the MOGI location by 5.2 kilometers. So the location is now centered in the middle of the Unimac Island, which is the name of the island where Okmok is located. So it's shifted, and then we move it from north to south, just like we did on the first column. And in the bottom column, we horizontally shifted along the eastern direction the location of the MOGI source, and then we now by another 5 kilometers, and now we are shifting the location of the source to the north, 16 plus 5 kilometers plus 5 kilometers. So what we can do in here, we can do a simple example, and let's say what happens if we make the source depth, let's say we are going to copy this line, and let's make it deeper. Let's say 10 kilometers, a very deep source. And let's see what happens. Essentially, when you make it quite deep, very deep, the predicted ground deformation, it is almost, you barely observe it with the InSAR data given a fixed location and given that source volume change. So one assignment that you will have to do, we will get back to the original volume change, sorry, source depth. An assignment that you will have to do is to change the model parameters for the source depth and for the source volume change, and take a look at what happens. And you will have to do it for several combinations of model parameters, create the figures, and check what happens when you generate that. So those are questions that you will have to submit for the Moodle on the Moodle platform within, I think, this afternoon. So we will skip to solving the inverse model. So an inverse theory is just a fancy way to call it's a fancy model. It's a fancy, in my opinion, I am not a mathematician, so I call it a fancy name for just doing something very simple, which is take a model, vary some parameters of the model, and use it to explain some data. So what we had to minimize. Oh, what did I do? I think I did something. Yeah, now it's working. I think I'll double click and I enter the editing mode. So what we're doing is take the predictions of the MOGI model for a given set of model parameters, again, horizontal location along the X and Y direction, source depth, volume change, calculate the forward model, subtract the data, that will give you a number, which is the residual, make it square, so the residual is positive, and add all those numbers. Essentially, we want this number to be this function to be as smaller as possible. In some formulations, you can divide it by the number of pixels. You can weight it by the uncertainty in your data with a diagonal or non-diagonal data covariance matrix. And when we minimize this function, what we are doing is just using a least squares inversion to calculate the best fit model parameters. So how this is done, there are all sorts of algorithms to do this. Some super fancy Bayesian Monte Carlo Markov chain inversion, which I think are just too complicated for a very simple model like this, to the simplest way of doing this, which is just fix some parameters, for example, the source depth, the volume change, and then loop over the model parameters that you want to fit. which in here are the horizontal location along the X and Y direction. So we need to calculate a forward model, GM, for all combinations of model parameter, subtract the observed interferogram, square it, so this difference will be a positive number, sum them, so we will get a single number, and just find the combination of parameters that provides the minimum value for this misfit function. This is just a mathematical criteria, and this is just telling us that regardless of how realistic or unrealistic the model is, it must explain the data. Realistic or unrealistic at this point is not a criteria that is used in the modeling. We are only using a combination of parameters that will explain the data. That's all that inverse theory does. For some more complicated formulations or more realistic, like Bayesian formulations, you can incorporate the uncertainty in the epistemic uncertainty, or how realistic or unrealistic are these models. But that's beyond the scope of this particular example. So the next code, what it does, it will loop along different combination, again, fixing the source depth to 2.58 kilometers, the source volume change to 0.0034 cubic kilometers, sorry, and then looping to these nine values for the horizontal location of the module source, we will calculate the residual, the misfit maps, and this will take a few seconds just to see how they look like. Yeah. So what we did in here is, again, take the original interferogram, provide a location, horizontally shift along the northing location of the module source, then shifting to the east, then shift to the north, and then shift to the east and shift to the north, and find the model that has the smallest misfit function. Just by looking visually at this data, we do observe that all these models have a positive lobe and a negative lobe, except for the model in the middle that shows essentially no positive, no strong positive, and no strong negative lobe. So this is from this 3x3 combination of horizontal locations for the MOGI model, we are visually observing that if these are all the models that we have, this is the model that minimizes the misfit function, and therefore it provides the best fit to the data. Of course, you can do this. I mean, in this example, we only do it every 5 kilometers, but in reality, you do it over a much narrower space, so you can actually sample very well the different values of the misfit function, and that can take a long time depending on your computer and how many model parameters you have. So what we do now is to grid search them. It's to run a grid search, which is, again, is just by looping at the different X, Y, and YS values for the horizontal location of the MOGE source. You can see here that given a fixed 2.58 cubic kilometers, sorry, 2.58 kilometers for the source depth and 0.0034 cubic kilometers for the source volume change, we are looping at different model parameters. So the code, what it did, it found that given a fixed 2.58 given a fixed depth and a fixed source volume change, it found that the best fit source is located at X equal 20.6 kilometers and Y equal to 21.8 kilometers. This is just done by calculating the misfit function for all the combinations of parameters, and then we can plot it. So the code at the bottom, what it does, it just plots the misfit function. And in a well-behaved, this is what is called a misfit function plot, sometimes a chi-square plot, depending on how you parameterize these things. And what it shows is that the misfit function has all sorts of values, but there is a minimum value located in the center. So this tells us that the minimum value is the value that minimizes the misfit function and that provides the best fit model parameters. The values are on a scale of 1 to the 7, 10 to a power of 7, and that's a very large number. So you can reduce it if you, for example, the misfit function divide by the number of pixels or apply some kind of metric to reduce the magnitude of the number. But the idea is that the number itself has to be as smaller as possible. If you weight by the data covariance matrix, this number will also be different. But what we care is just getting the smallest number possible given the type of the range of parameters that we are searching for. So we found a minimum. The other thing that is important, this looks kind of circular. You don't see like an elongated trend, like along this direction, or along this direction, or along this direction, or along this direction. And that means that the model parameters are not correlated with each other. Certain combinations of model parameters are correlated with each other, and that is something that you will find when at the end of this activity, you will have to calculate the misfit function for the source depth and the source volume change. So let's go to the next part of the code where we compare the predicted, what are the synthetics, how the synthetics look like. So this was our original interferogram, the graph interferogram. Here is the synthetic interferogram predicted by the best fit MOGI model. And visually, just by comparing them visually, you can say that they look kind of similar. Again, this is a model. A model is some simplification of the reality, so it will never look exactly the same as data because models are simplifications. But also because data has noise. Also, different sources of noise that other instructors will guide you through along this course. And this is one example. This yellowish pattern is an example of a residual source of noise. We are not trying to model that, but the code essentially, we do not want to model the noise. We only want to model the signal. And by just visually looking at the data and comparing with the signal in either ungraph or graph interferograms, they look fairly similar. And and that means that the model explains very well the data that we are presenting in here. The final panel essentially shows the data that is not masked. And this is something that you do because you calculate this over all the pixels. That's easy to do on a computer, but you have to mask to compare the data because we're working in an island and InSAR, for example, cannot measure ground deformation over the water. So we need to mask all the areas that have water outside of the island and in the regions where the coherence was lost. And that's because the backscattering properties of certain pixels changed between the 2 years where the first acquisition and the second, where the first image and the second image were acquired. So we are going to plot finally the residuals, and to take a look if there are additional signals in the data that are not modeled using MOGI. And in here, for example, because the data has this yellowish signal, yellow-orange signal with an amplitude of about 10 millimeters in the radar line of sight, that is not explained by the model. So that shows up in the residual, which is just the difference between the data and the synthetics predicted by the best fit model. It shows up both on the graph and in the graph data. And we do observe some signals in the middle of the Okmok caldera that are probably due to changes in the elevation that resulted from the extrusion of a lava flow in 1997. And those changes in elevation result in what we call a DEM error, an error in the DEM because the DEM that was used to process the interferogram did not include that lava flow. So probably these signals that we do observing here that have a relatively large amplitude, several centimeters, result from a DEM error, in the middle of the caldera. So this is not really ground deformation. This is a change in topography, and that propagates as an apparent displacement, even though it is an error in the DEM that results from the change in the topography. So just to wrap this up, because I have about 3 minutes left, one exercise to suggest is to think whether residuals are not zero. And one very important point in INSAR is that atmospheric signals need to be accounted for, because if you do not account them for, you can interpret them as ground deformation. This is an example on the Big Island of Hawaii, an interferogram that shows positive, something that looks like ground deformation, a positive uplift in the radar line of sight at Mauna Loa and Mauna Kea volcanoes. But when you correct them, when you correct the data or try to correct the data using an external atmospheric model, these signals can be completely explained by this atmospheric model, and that results in that, and that means that the data, that the signals that you're observing in the original data are not real ground deformation. These atmospheric models are not perfect. They do not correct everything. For example, you have some signals in here that are not included in the correction predicted by the atmospheric model. So these models can correct a lot. In some cases, do not correct anything. That depends on where in the world you are. They do not have the same temporal or spatial resolution than INSAR. So that's one source of uncertainty. But this is something that you need to think about when you work, especially in regions with high relief, to assess if some of the signals that you do observe, in this case, it looks like 5 centimeters, are real apparent ground deformation or just an atmospheric noise. So to wrap this up, you will have to run the grid search again, but in this case, to search for the best fit source model, source volume, source depth, and the best fit source volume change by using fixed locations for the, I did double click on that, by using fixed horizontal locations at 20.6 kilometers and 21.8 kilometers for the easting and northing component. So you will have to modify this code on your own to run for the best fit model parameters. You have to provide the best fit model parameters, and you will have to provide a plot for the misfit function, just like we did for the horizontal components for fixed source depth and source volume change. So I think I made it right on time. So I'm happy to take questions about this quick tutorial on how to model an interferogram using MOGI. Yeah, I'm open to have more questions, or if people want to take a break, or I don't know.
Well, there's time for questions and also a break.
Yes, both. Yeah. I mean, I tried to make it on time, and I think I did it.
You did great. We have never
Yes.
been this much on time ever on day one.
I just don't like to overextend over my allowed time. If something was not clear, I can explain it again.
And of course, also this could be a good topic for office hours.
Yes.
This evening or tomorrow morning.
Yes.
If you want to have more explanation of this and how to do the homework.
Yes. Yes.
Well, if there are no questions, and I'm not seeing any, I think we can go on break until noon Pacific time. I don't know if anyone with the controls. All right, a question has appeared in the Q&A. We can answer that during the break.
So the question by Ganiyat is, how do you know the residual seen in the model is just due to noise, since you don't have an atmospheric model for that area? Okay, there are atmospheric models. Those models are calculated all over the Earth. The data in here was not corrected by an atmospheric model, and the reason why we know that the data is ground deformation and is not an atmospheric model is the following. So I will share again my screen. When you look at some data, you can see that the amplitude of the signal in the middle of the volcano is significantly larger than anything else. You are looking at large values over a very specific region, And in this case, this is a value of several centimeters over a background value that is at most, in this case, 10 millimeters. So more than 3 centimeters over 1 centimeter. So what we are looking is a specific pattern in a very specific region, and because it is large, it is significantly above the background values of the data, and it does not show up everywhere. That means we're using a quick criteria that is ground deformation. This signal is also observed in many different interferograms that span the same time, the same 2 years, calculating different images, also calculating the images from different radar satellites. And because INSAR is just a measuring tape, all interferograms are just essentially, you're using a digital measuring tape that has different uncertainties, and because all the radar signals are showing, all the radar satellites are showing the same radar signal, that is shown up in a paper by Sean Lu and Dan Reason from like 15 years ago, we're very sure that this signal is ground deformation. And because this pattern is also different, these atmospheric patterns are different when you calculate other interferograms, because the atmospheric signals change a lot between different interferograms. There is another question, I think. And because because we're in a volcano, most of the ground deformation is due to a pressure source, and we know that pressure sources essentially explain kind of symmetrical patterns. They do not have the capabilities to explain that. And because we also have, again, other interferograms, this signal is not observed in the other datasets. So we're pretty sure that we do not need to model that. When you look at several tens of thousands of interferograms, you get very used to realize what is signal and what is noise, and that takes a while when working with data. You can also calculate the data variance over the regions that do not have the expected ground deformation signal, and you will see that the data variance will change when you calculate other interferograms. So that variation means that the signal is uncorrelated in time, and that's a characteristic of atmospheric phase delays.
Okay, let's have a little break.
Yes. Okay. Sorry for the long explanation.
Come back in 6 minutes.
Okay.
We'll have some INSAR theory.
Mm-hmm.
Well, that was nice. Welcome back, everyone. If you're not back, you should get back soon, because Molly's here and she's going to tell us about INSAR theory in a lecture. Whenever you're ready, Molly, take it away.
Sure. Let me share. Okay, I think you guys should be able to see. So I'm Molly Zebker. I'm at the University of California, San Diego. I just want to acknowledge that this lecture on INSAR theory was originally developed by many others, mainly Paul Rosen and Scott Hensley. And previously was taught by Ann Chen, so she contributed quite a bit to this presentation as well. So you guys have heard a little bit about INSAR techniques and have heard some of the terminology through Gareth and Francisco's lectures. But I want to give you a little bit more background and technical details on how this technique works, because you'll be using it throughout the duration of this course. So let's, if my slides advance, okay. So I want to start by actually introducing synthetic aperture radar, or SAR. So SAR is an imaging technique where a satellite will fly over an area of interest and emit a series of pulses on a moving platform, which then synthesizes when the pulses come back to the satellite, the pulses are then synthesized to produce a two-dimensional image like you see here in the phase and amplitude values. So this is called synthetic aperture radar, and it was first demonstrated with fine resolution in the 1950s by someone named Carl Wiley and his team at Goodyear. So the way that this technique works is the satellite flies over an area of interest, sends out a radar pulse, which travels to the ground at pixel A that we see here, and then it comes back to the satellite. And the received radar echoes, as I said earlier, contain two values, an amplitude, which you can see by the grayscale image, and phase or phi, which are stored as single look complex radar images. So the amplitude of this signal depends on the total energy that's reflected back from the ground. And the phase of the signal is related to the distance between the satellite and the ground pixel, as well as the distribution of the centimeter level scatterers in each ground pixel. So these scatterers are random in a single image, and that's why our phase in this example here looks like television static or random noise. So if we take a look at the electromagnetic spectrum, just to give us an idea of what kind of pulses we're transmitting to the ground, we are actually in the microwave frequency out here, with the most common satellites transmitting X, C, and L band wavelengths. So here you can see that ranges from about 3 to 20 or 30 centimeters. So that's the wavelength of the signal that is transmitted from the radar echoes. So we have a couple other kinds of sensors that we have plotted on here just to give you an idea. Optical imagery is in this visible light spectrum, so much, much smaller. We have thermal infrared, just slightly larger than the visible wavelength. And then we have some radar altimeters, which are a little bit smaller than the radar echoes that we're sending out for SAR or InSAR satellites. So what is in a SAR image? So we saw that little example of the amplitude values, which depend on the energy reflected back to the satellite. Here are 4 examples of different kinds of backscatter, and you can see that they vary a lot based on the ground conditions. So the radar is imaging an area on the ground, and then the ground pixel is reflecting energy back to the satellite. And so for an area in Louisiana, under normal conditions, you can see that the water or the flooded areas have really low energy, so they're all black, whereas some of the roads or built land are this higher energy, light gray or white regions. So on a day where we might have lots of wind, we get a little bit more reflectivity on the water, because instead of the water being smooth, there are some waves to it. And so that can contribute to increased energy coming back to the satellite. So you can see these flooded regions are a little bit lighter in color. They're not quite as black. On a day where it's windy and maybe it has flooded this entire region, you can see that there's more water all throughout this area, but it's not quite as dark as day 1. So that indicates that it's possibly windy or it's raining. So it's creating different surface scattering on the ground. And then we have an example for day 4 where it's less flooded again, and the water areas are pretty dark. So this is indicating that it's a little less windy and the conditions are more like that first day. So that was an extremely abbreviated intro to synthetic aperture radar, or SAR. But it's critical for actually understanding how InSAR works. So SAR is when, or operates when the satellite passes over an area of interest one time. But say we have a satellite come over an area of interest a second time, And then we have a technique that is derived from SAR called interferometric synthetic aperture radar, or INSAR. So here you can see the first satellite orbit at this position 1, and it will send out radar echoes and collect a set of amplitude and phase values. Then at a later time, T2, the satellite will fly over again at approximately the same location as the first one, and it will acquire a second set of amplitude and phase values. And so this time, what we can do is we can calculate the difference between the phase values of our first acquisition and the second acquisition. And we can do this for every ground pixel that we're imaging. And then we can create an interferogram, or a change in phase between our two acquisitions, that actually looks like some type of data, or some kinds of fringes and colors. So that change in phase, if you do that over every pixel, that is called an interferogram. So the way that we form these interferograms is we take our two radar images, C1 and C2, and as I said earlier, each of these radar images contains phase and amplitude values, which are stored as complex numbers. So they have a real and an imaginary component. And if we want to compute the difference between these two complex numbers, we multiply the first image, or one image, by the complex conjugate of the second. And then we can create an interferogram. So this is just showing that each image alone, the phase value will look like random noise. But if you find the difference of these two complex images, we can start to create some of these spatial patterns that maybe we can begin to interpret. So here is a simple diagram of imaging geometry for two satellites, or two positions of the satellite. So if the surface scattering doesn't change much, we can relate the range, or the distance from the satellite to the ground at point A by this value rho. So this is our range 1. And we have a second set of ranges from our satellite position at time 2. And here is our range plus some difference based on the spatial difference between the two satellites in time. And what we can do is we can go through some high school trig, and we can link the difference in these range measurements to the topographic height of the pixel P on the ground. So here are a couple of equations that can just relate this imaging geometry to be able to solve for the height of any pixel we're imaging on the ground. So what we have here is that we're actually measuring the change in phase between our two radar acquisitions. We know how high the radar is flying. We know how far apart the satellites at different times are, which is this B. We know what some of the angles are through this geometry, and we know the approximate range distance. So we can actually solve for the height of every pixel on the ground. So this technique was first used in the 90s to measure topography everywhere. So this was the first application of the INSAR technique. So there are a couple of details that are necessary to understanding the satellite's performance. So if we we'll zoom into this part of our imaging geometry. And here, this was our satellite at time A, satellite at time B. We can draw a couple of triangles, and we come up with two different values. So the first is the parallel or the parallel baseline. So how far apart the satellites will be along this edge of the triangle. And so for topography mapping for INSAR, we make some assumption, which we call the parallel ray approximation. So this assumes that the radar looks from the two satellite positions. The difference between the range to the ground is much, much smaller than how far the radar is from the ground itself. So based on this assumption, the distances are approximately the same. So it will simplify our phase to topography math. So it replaces a law of cosine calculation with a linear projection. So we can more easily compute topography over the ground. So this is valid for systems where the radar is flying about 800 kilometers high, and this parallel baseline is on the order of 100 meters or so. So the second baseline that we have is the perpendicular baseline, which we have expressed here. So this is important for understanding the quality of our phase measurement that we may have in our interferograms. So there's one thing that we can compute from the perpendicular baseline. So we can compute the maximum separation between the two satellite positions before our interferometric phase, where the correlation between them drops to 0. So this is something called the critical baseline. So it's how far apart these two satellites are. So from this diagram here, the two satellites will image an area on the ground. Say this is a single pixel shown by the boxes. If the look or the position is too different or too far apart between our two satellite acquisitions, we may not be able to recover coherent phase. So if the change here, the change in phase between this 1 pixel is greater than 2 pi, then we'll have 0 correlation and we won't be able to get a delta phase measurement between them. So this critical baseline is really important, and we can actually compute that for different satellite systems through this relationship. So we have the wavelength of the radar here. Rho is the range. R is the range resolution on the of the satellite, and cosine theta, where theta is the incidence angle. So here are a couple different incidence or look angles for different satellite systems. The earliest generation ERS NVSat had a critical baseline of about 1 kilometer. ALOS has a couple of different modes where the critical baseline is 6 to 13 kilometers. So again, this is how far apart the satellites can be in space before the phase correlation drops to 0. So we can compute these values for the Sentinel-1 satellite. Here are the typical values for all of these parameters. And through just plugging it into this equation, we can come up with a critical baseline of about 5 kilometers for Sentinel. So this means we need the satellite to be less than 5 kilometers apart every time we make a pass to be able to interfere our phase values and create an interferogram. So for topography mapping, if this perpendicular baseline is larger, it will increase the sensitivity to height. But if it's too close to that critical baseline, it'll introduce decorrelation, and we won't be able to make any reliable measurements. And for deformation mapping, we want the perpendicular baselines to be as close to zero as possible to maximize our phase coherence. So now that we can compute the height of every point on the ground, and we know what our critical baseline is and what our perpendicular and parallel baselines are, we can actually solve for topography from that change in phase between our two acquisitions. So here we know all of these parameters, and we do something called subtracting a flat Earth fringe. So this accounts for the predictable fringe pattern in an interferogram that's caused by the curvature of the Earth. So the Earth is referenced to some ellipsoid, and this is the expected amount of phase values due to this Earth's curvature. So once we subtract off the flat Earth fringes, we can actually solve for topography. So this technique has been done several times. One of the first was in 2000 when the Space Shuttle Endeavour flew with two antennas, one attached to the main shuttle and an arm that was extended about 60 meters off the main shuttle. So this mission was called SRTM, or the Shuttle Radar Topography Mission, where these two antennas are the two locations of those dots in our imaging geometry. So here that baseline is about 60 meters. So the data acquired from this mission were assembled to create a digital elevation model with about 30-meter resolution and 10-meter accuracy. But nowadays, with more advanced positional and orbital controls, we can actually fly two satellites. So we have one satellite here, another following close behind here. And this is called the Tandem-X, which was a TerraSAR-X add-on to measure digital elevation models or digital elevation measurements. So here, the Tandem-X and TerraSAR-X satellites fly approximately 500 meters apart. So this extends that perpendicular baseline. So as I said earlier, that's desirable for mapping topography. So with this advancement, we now have digital elevation models with 12-meter resolution and about 4 meters accuracy. So there are a couple of other ways that you can create digital elevation models. One is from optical imagery, which will basically capture overlapping pictures of the Earth using satellites or airborne or drone sensors. And you can measure the pixel shifts common areas on the ground, and then compute the digital elevation model from that. You can use laser profiling image instruments like LiDAR data from aircraft or satellites. And these techniques will use laser beams that are pointed directly at the ground that will reflect back off of the Earth's surface and create lots of points or profiles, so single tracks across the Earth. And this will include the heights of buildings, vegetation, and the ground, but doesn't quite cover the amount of spatial resolution that we can get from radar interferometry. So one of the advantages of using INSAR is that you can map large areas on the ground pretty efficiently with these satellite systems. So this is an example of a digital elevation model of the US. So you can see higher topography areas in brown here, some lower topography areas seen as the dark green. So this is the Central Valley. It is sunken down from the neighboring Sierra Nevadas just off to the east. So that was interferometry for topography mapping, which was the first application of INSAR. So now we want to look at INSAR for mapping surface deformation. So we have the same geometry that we saw earlier. I've changed the convention of some of our terms now, but this is the satellite position at time 1, the satellite position at time 2, perpendicular baseline, parallel baseline. And here you can see the range from the satellite to the ground at time 1 and time 2. So at time 1, if the ground is at point A, the satellite will record the range during this time. And then if the ground moves between our two acquisitions, we get a phase value for A prime at that second time. So the difference between A and A prime gives us is related to the amount of deformation that has occurred between the two time periods. So we can express this as our change in phase between our two times, 2 and 1. So this can also be written as delta phi. And that includes a component with our topography, which we just learned that we can solve for using these same techniques, plus the amount of deformation that has occurred between the two times. And this is scaled by 4 pi over lambda, which accounts for the two-way travel time and propagation of a radar echo with a wavelength of lambda. So we can compute that change in phase for every single pixel on the ground, and we can form something called an interferogram, which we see here. So this was the first interferogram that was produced, and it shows the amount of deformation that occurred during the 1992 Landers earthquake. That was a magnitude 7.3 just outside of Los Angeles, and it caused tons of damage. So this image was first published on the cover of Nature in 1993, and at the time provided the first image of an earthquake seen from space, and it had denser spatial sampling than any other geodetic imaging technique with meter level resolution. So here we have the fault trace right in the middle of our interferogram, and it spans about 85 kilometers just to give you an idea of the spatial scale of these interferograms. And then all of these colorful fringes, which go from red to yellow to green to blue back to red, emanate away from the fault trace on either side. So here, one fringe is from red all the way back to red, and that represents about 2.8 centimeters of displacement along the radar's line of sight for this wavelength. So ERS was a C-band radar, so we have a radar wavelength about 5.6 centimeters. So one of the things we can do with these interferograms is we want to be able to interpret how much displacement has occurred. And one way we can do that is by counting these colorful fringes. So from the fault trace out to the far field of this earthquake, we have about 20 fringes. And for this satellite, that is equivalent to about 5.6 centimeters. So with earthquake images, we get lots of these dense concentric fringes. that you can count to approximate or measure how much displacement has occurred. But for some other applications or smaller displacements, you may only have one or two fringes. So to summarize some of the sensitivities of these two applications of INSAR, we saw that we could measure topography with meter level accuracy, but we can measure displacement with centimeter to millimeter level accuracy because we're measuring the differences in phase related to the radar's wavelength and how that relates to other pixels in our scene. So from that interferogram example, we saw that we had concentric fringes like we see up here in this interferogram. So this kind of image is called a wrapped interferogram. So that means that our phase values only go from 0 to 2 pi. And when it exceeds more than 2 pi, it'll drop back down to 0 and it'll continue in this sawtooth or wrapped pattern of phase. So phase values don't actually give us absolute deformation because the phase is only known modulo 2 pi. So we have to perform a step called phase unwrapping so we can know how much absolute phase there was. So that exercise that we just did by counting the fringes in the Landers interferogram is essentially what phase unwrapping is. You're basically counting the number of fringes and then stacking them up. So every 2 pi fringe can be added together to give us an unwrapped phase. So hopefully this is a little bit of a visual representation of that. So we're basically adding integer multiples of 2 pi, which represent each fringe in an interferogram. So this is an example of a wrapped interferogram with all of those fringes again. And then when we unwrap it, we get this actual displacement value from our phases. So here, the line of sight displacements are now in meters instead of radians and in wrapped values. So the unwrapped images are much easier to interpret, and for areas with lots of fringes or other noise, it's much easier to interpret these unwrapped images. So in ICE, there is an algorithm called Snafu, and this does the unwrapping for you. It has lots of different parameters, but one could start with the default parameters to try to unwrap our phases. So now that we have our interferograms and we've seen how to unwrap them, if we want to interpret our data, there are several contributions to our phase signal that we need to consider or at least be aware of. So if we start with our change in phase, so this is what our interferogram measures. The term that we typically want is this delta D, so the deformation that has occurred between our two images in the radar's line of sight, and it is scaled by our two-way travel time of the radar's wavelength lambda. And then we have additional components that are related to digital elevation model errors. So remember that we have accuracy of our DEMs on the scale of 5 to 10 meters. So that could contribute to some phase in our interferogram. We have atmospheric errors. So some due to the troposphere, which we'll talk about in a bit, and ionosphere. There might be contributions from orbital errors, decorrelation. So this could be related to that critical baseline we saw earlier, or related to how the surface scatterers change between our radar acquisitions. We have unwrapping errors. So if that unwrapping step fails, or we add an incorrect multiple of 2 pi, we'll get some phase related to that. And then some kinds of thermal noise, which are much smaller. So the signal that we're measuring encompasses lots of these other signals. So once you make an interferogram, it's often hard to directly interpret that. And I think there are a couple of lectures that will go into more depth about that too. So one of those first errors is from orbital errors. So this comes from small inaccuracies in the exact position and velocity of the radar satellite when it takes or when it acquires the images. So these tiny little mistakes in the or inaccuracies in the satellite's position may produce these smooth ramps of phase across our radar or across our interferogram. So here we can see there's a phase ramp going from yellow to blue to pink back to yellow, going across our whole scene. And oftentimes when you see that, especially with the shorter wavelength interferograms, those are related to orbital ramps. So depending on what kind of signal you're looking for, if you're looking for earthquake signatures or volcanic signatures, you may be able to remove a ramp from your interferogram to actually get the signal that you're looking for. So this is an example of an L-band interferogram with an orbital error. And after we remove the ramp, this slight aquifer uplift signal starts to pop out. So here that small subtle signal was completely buried by the orbital ramp. So another form of error that one might see in an interferogram is due to those inaccuracies of the DEM. So this is an older version of a DEM, and you can see outside of, I assume this is a volcanic region, you get these extra fringes or phase values associated with the inaccurate DEM. But when we use the SRTM, or in even an updated one is the Copernicus DEM, you can see that the phase outside of the volcanic area is much less. So we have less DEM error contribution to our interferogram. So I mentioned a couple of different kinds of atmospheric signals. One is from the ionosphere. So the ionosphere contains electrons. So when the electrons are excited, we have this stronger total electron content, or the stronger gradient. And that can cause some of these extra fringes in our interferogram that might look similar to those orbital fringes. But when it's really bad, the ionosphere can actually lead to mislocation of our pixels in in a radar image. And you get areas of really low correlation, like we see in this red circle. So on the right here, we've computed the misregistration or offset of pixels, and on either side of the large TC gradient, you can see mislocation by about 6 pixels going across this area. So if similar features on the ground are mislocated, you won't be able to interfere them, and that's why we get this drop in correlation. So we also get noise from troposphere. So this is this occurs in your interferogram when you have changes in temperature, pressure, or water vapor, and when the satellite will send out a radar pulse, and it will travel through these changes in temperature, pressure, water vapor, and create phase delays. So the phase will have additional contributions to these changes. And because troposphere changes over time on scales less than a day, when you have new radar acquisitions, you'll have different troposphere contributions, and the phase delays can add anywhere from 0 to 15 centimeters of phase to your interferogram. So troposphere can lead to either stratified, or there can either be stratified troposphere, which is related to the topography. So areas of high elevation or low elevation might have more or less troposphere. And then there's also a component that's random in time. So this is the turbulent troposphere, which is harder to model and remove. So you saw this example that Francisco just showed over the big island of Hawaii. You have the two large Mauna Loa, Mauna Kea. So these are high elevation, and here we have extra phase measured on top of these peaks. So when we have this stratified troposphere that's correlated with topography, we can try to model it or do a regression of phase versus elevation and subtract that off from our interferogram to reduce that kind of noise. And then this is an example of the more turbulent kind of troposphere we might see. So this is less. This is not correlated with topography and is just different pockets of different kinds of weather. So an additional component that's important for understanding INSAR is called correlation, and this is the measure of the phase quality. So when the correlation between our two SAR images is really low, this means that the pixels are completely decorrelated, and it'll look like this random noise that we saw from the individual SLCs. So this means that areas on the ground between our two satellite images are completely different. So think of a farm. If you take if you acquire a radar acquisition at one time, and then you go and you till the ground and you've changed the cover completely, and you acquire a second acquisition, the phase may look like this, where it's completely decorrelated. But then areas over bare rock or roads, or areas that don't change very much, we have high correlation. So this contains the kinds of topographic and deformation data that we want to be able to interpret. So the correlation can be calculated when we generate multi-looked interferograms. So when we essentially do, or you could do a boxcar filter to take to downsample our single look complex images. We can average a bunch of our pixels and compute the correlation at each pixel. So this is just showing ensemble averaging of the relationship or the correlation between the pixels on a ground. And if we average that in a moving average or a boxcar filter, we can compute the correlations. So this is an example of correlation from an interferogram where the satellites acquire images 1 day apart. So you can see that across the whole scene, the correlation's pretty high. Maybe some of these agricultural fields have lower correlations, around 0.4. But if we try to solve for correlation over a 6-month time period, the areas that will change a lot, like the agricultural areas, have really low coherence, closer to 0 or 0.2. And then areas of higher coherence or exposed rock will have this higher, brighter color correlation. So we want data that is closer to this 1 correlation. So our correlation comprises a couple different components. We have the thermal correlation, which is the electronic changes in the radar system, spatial correlation, which is the change in sensor locations, so due to rotation and viewing angles. And then we have temporal correlation, which is the decorrelation from changes in the surface scatters. So this temporal correlation is often what we see due to things like agriculture, farming and tilling of the land. Or if there's a landslide, then you would have decorrelation between our radar images too. So this is an example of how different wavelengths have different correlations or coherence, a similar metric. So on the left here, we have a C-band interferogram over Kilauea in Hawaii. And here, these dark areas are vegetated regions where there's really low correlation. So that means that the vegetation has grown quite a bit from between the 2 radar acquisitions. But with the L-band radar, we have a longer wavelength of about 4 times longer. And when even when there's vegetation growth, it can maintain coherence in some of these vegetated areas because it penetrates through the vegetation more effectively. So there are advantages to using different wavelengths. In this example, the longer wavelength means you'll measure fewer fringes. So you can see fewer fringes across the L-band interferogram than across the C-band. And so this is typically easier to unwrap. But then, and it maintains coherence better in vegetated regions. But at L-band, which we'll see later, it is more susceptible to some of that ionospheric delay. So this is just giving you an overview of the different wavelengths for different targets. So depending on what kind of application you have, you might want to use different satellite systems. X-band will return radar echoes from the treetops and smaller branches. C-band with a slightly longer wavelength will penetrate through that canopy and reflect off of the larger tree branches. And then L-band with the even longer wavelength will more effectively penetrate through the canopy and reflect off of the tree trunks and the ground and the larger branches. So just to give you an idea of what this looks like in real data, we'll look at the magnitude 6.3 earthquake in central Italy from April 2009. Here we have the epicenter. This is, I believe, this is the Cosmos SkyMed X-band interferogram. And you can see out here, the phase is completely decorrelated. We can't make out spatial patterns like we see maybe in the middle, but you can see some of these fringes in the middle of our interferogram. So the satellites that use X-band radars are TerraSAR-X, Cosmos SkyMed, and then some of the commercial satellites from ISCE and Capella. So remember this image. If we look at C-band, this is from NVSAT. Our C-band radars are from ERS, RadarSat, NVSat, and the Sentinel satellites. So you can see that there's still areas of decorrelation, but now we're seeing these concentric fringes from the earthquake signal. And we're recovering more reliable phase in the C-band interferogram than we were in the X-band. And then finally, we can look at an L-band interferogram. This is from ALOS-1. This is from the Japanese Space Agency and some of the other satellites that use L-bands, an L-band radar, and notably the new NISAR mission, which we will talk about a lot more in the next few days, uses this L-band wavelength. So here you can see there's coherent phase across our entire interferogram, and we have fewer fringes associated with the event because it's this longer wavelength. And seeing some of the extent of this earthquake is much easier through this L-band analysis. So just to conclude and summarize, the different systems. This is a comparison of C-band, L-band, and P-band, which is much longer wavelength from 30 to 100 centimeters. Looking at the same area, you can see that there are different amounts of fringes and different correlations. So typically the longer wavelengths will have higher correlation in these vegetated regions. But this is just a nice comparison of the three different wavelengths that we might use. So I will end on that for now, and happy to take any questions in the chat, or I'm sure many of them will be answered throughout the duration of this week.
Awesome. Thanks, Molly. Yes, we have time for questions. If anyone has one that hasn't already been answered. It was obviously so clear that everyone is very satisfied.
Great.
In which case, if there is no one who wants to chime in, we can go for a break for another 10 minutes or so, and then when we come back, it'll be me up with an interferogram for everyone to interpret, which will be exciting.
I just wanted to mention that NISAR now uses the name coherence instead of correlation. That's a change that's happened in the last decade or so, that a lot of people are now using the word coherence instead of correlation. It really means the same thing, it's just a different word.
Sometimes calculated slightly differently, but low coherence and low correlation are basically occurring in the same places. Right, let's go. Let's come back in at 1 p.m. Pacific time. Well, welcome back, everyone. One more thing to cover today, and that is interferogram interpretation. And for this, I will share my screen and show you what we're dealing with here. This is section 1.4. So here's my screen. I hope that's a useful size and you can read everything all right. And I will open in Open Science Lab the notebook for this section. So it's under 2026 ICE Plus and 1.4, interpreting a co-seismic interferogram. And if you go through all of that, you should find your way to here. And what this is going to describe is what we're going to look at here. And we have an interferogram of an earthquake that happened in 1995. So this is actually a pretty old interferogram, but it's a nice example because it's big enough to be slightly complicated without being like unwieldy, having too many fringes to look at. But it's an earthquake that occurred. It's an interferogram of an earthquake that occurred in the region of Western Turkey near the city of Dinar. And that area in Turkey is an area under active tectonic extension due to the interaction, the subduction of the African plate under Europe at that location, which causes, amongst other things, volcanism in Greece and also a lot of large earthquakes. And this earthquake has a significant amount of deformation recorded in it. It also shows various of the things that Molly just talked about, including decorrelation. And without further ado, I'll show you what it looks like. Here it is. So on here, we've got a color scale. We've got a color scale going from 0 to 0.028 meters, so 2.8 centimeters or 28 millimeters per cycle. If you remember Francisco saying this earlier, this is half the radar wavelength. So each cycle of colors from blue to red indicates a deformation of half a radar wavelength, or a change in distance between the satellite and the ground of half a radar wavelength. And it's half a wavelength because what is happening if the ground moves is that the two-way path between the satellite and the ground and back to the satellite is changed by a whole wavelength. And that's why you get one full phase cycle of deformation for a half wavelength of deformation. What else? Oh yes, I told you earlier that you really need to look at the figure captions to tell what is going on here. And so here is the critical sentence in the figure caption saying each cycle of colors from blue to yellow to red indicates an increase in distance between the satellite and ground. So does this mean we are measuring ground displacement or range change in this interferogram from that description? I should turn my chat on so I can actually see if anyone answers. Yes, if the chat is live, type the answer, or if anyone is brave enough, maybe raise your hand and we can ask you to say it out loud. Anybody? We have one person saying topography, which that's not range change or ground displacement. One person saying range change, which is to say that when you go one cycle of colors, the ground is moving further away from the satellite, and that indeed is what this says. So each cycle of colors from blue to yellow to red indicates an increase in distance between the satellite and the ground. So yes, that is range change. Great. So yes, so when you see these phase cycles, you can see one here. This fringe boundary marked here goes from blue to yellow to red. The ground is moving further away from the satellite as you move in that direction. Okay, so you have blue, yellow, red, blue, yellow, red, blue, yellow, red, blue, yellow, red. So as you move along the trend towards the middle of this set of fringes, each one of them is showing that cycle of blue to yellow to red.
Gareth?
Yeah, I saw a hand up.
Yeah.
Go for it.
Yes, so my question is, when you say it's a range change and it goes away from the satellite, right?
Yep.
So that means the satellite is, I want to just confirm. So satellite is moving from south to north and it's moving away from it. So it's looking towards east, that what I think she explained, that it is distance between the movement and the satellite change. And then there are two different uh, satellite came to the same place two different time, and there is a difference between them. So these fringes are showing that in both time the satellite was looking away. This was away from the satellite, right?
Right, so the way to think about this, I didn't actually mention the direction of the satellite flight. In this case, we're just going to assume that what we're seeing is vertical. The EOS satellite, which is what this is, what the satellite that acquired this data, EOS-1, had an incidence angle of 23 degrees to the vertical. Again, I think Francisco mentioned that. So, like,
Yeah.
mostly it was sensitive to vertical motion. It was somewhat sensitive to east-west motion, but less so. And for the simplicity's sake, we are going just to assume that the deformation is vertical here. So if the range change is positive, the ground is moved further away from the satellite, we're going to take that to mean the ground went down in this case. But that is also a simplifying assumption. Yeah, and you're right that you could actually detect other things potentially. But for now, at least, we will just assume
That's
everything is
vertical.
vertical.
So, okay. Yeah. Thank you.
Thanks for the question. I'm sure other people had that question. Okay, so that's what we're measuring. We're measuring vertical height change of the ground, and there is a suggestion that we see increasing range change as you move from the outside of the pattern to the south inwards. All right. So what we also know, and what is also marked on here, is this black line here is the location of a known fault at the surface called the Dinar-Chivrel fault. And we also know that this moved during the earthquake up to about 30 centimeters. So that's information that we have. And if you read the text in more detail, you'll find out all about that. And also we know that this was a normal fault, which is the type of fault in which you have one side move down appreciably compared to the other, which is common for the style of tectonics you have in Western Turkey, which is tectonic extension. And the first thing you're asked to do here is to count the number of fringes, just to know how much deformation occurred in this in this earthquake. And you're asked to do that both on what we call the hanging wall side, which is the southwest side, and also on the northeast side, because the fault, as I said, goes through the middle here. And so I ask you to count these, and you can either do that on this image here. There's also a number of different versions shown listed here. You can actually open the PDF of this if you want to, and zoom in if that helps. You can also download the PDF to your machine, and you'll just by right-clicking on it and download, and then you can open it maybe larger in a different window if you want. But yeah, how many fringes do you think there are in this collection of fringes here? Again, it would be nice to have some answers in the chat, or if the chat's not working for non-instructors, but the Q&A I think would be a good place to put it then. So yeah, there's three questions you're being asked. Like, how many fringes are there? What total displacement does that equal? We can do that later. And what direction did the ground move? We have 20 and 21. 22. Any advance on 22? I think if we made like a histogram, it might center on the right number. 2, 3. It's also slightly difficult in that you can see that you can't always count directly through areas. You might have to put together several areas, like here there's decorrelation of the interferogram, so that might interrupt your ability to count the fringes in there. You might have to go a different path. And zooming in will really help. I'm not going to bother to do it right now, please. Whoever said 20-ish, I feel that. It's actually not straightforward to say that there is a clear answer that's correct, because they get very, very close together in here, and you might have to interpret. But yes, in the realm of 20 to 22, I would agree. So what vertical displacement does that indicate? Okay, one person says 20 fringes, a vertical displacement of 56 centimeters, which is 20 times 2.8. So yes, it's in that realm, between about 55 and 60 centimeters of deformation. And Manuel also says subsidence, which is right. The ground is going down. It goes blue, yellow, red, all the way down. Okay, well done. So now I'm going to ask you the same thing, but coming the other way. Starting over here at the X prime on the profile line and counting inwards here, you can assume that the end of the line here is 0 displacement. But how many fringes are there between here and, say, the fault? And what displacement do you have, and in which direction? The counting is easier, I think. Maybe the rest of it is less so. Excuse me. We have 1 to 2 fringes, some saying towards the satellite, some saying away. Yeah, again, you're going to have to kind of guess where the boundary is. Right down here, I'm given a 0 level for this side of the fault, where it's actually, I actually count half a fringe from 0 to the first proper fringe. So if you apply that logic, maybe this is also shifted by half a fringe. I'm going to look at people saying 2. Towards satellite, say a couple of people, 2 fringes. I might even go to say 2.5, because I think the first fringe is here and the second one is there, and then this is another blue here, and if 0 on this side of the fault is half a fringe away from the first sort of red to blue transition, this could also be half a fringe away from that. So I'm saying 2.5. 2.5 fringes is 7 centimeters. That's a nice round number. Is it up or down? I see there were a couple of votes for up. I also saw a vote for was down, so I'd like to see more of a consensus before I weigh in here. All right. Up, 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 up. Cool. That's a pretty resounding set of votes for up. Yes, and the reason why, of course, if you start over here and you're counting inwards, instead of blue, yellow, red, the fringes go red, yellow, blue twice. So yes, that's the opposite direction to blue, yellow, red. Blue, yellow, red is range increase. Red, yellow, blue is range decrease. So as you get closer and closer to the fault, you're moving more and more up. So congratulations to all who said up. Cool. Yeah, okay. Fantastic. Okay, so the next thing we want to do is to go a little bit further and to take this profile and actually make a an interpretation of the displacement as a function of distance along the profile line. For that, you'll find in the files here a grid which shows the distances, the locations of x and x prime, and the distances in kilometers along the bottom. If you actually were to print this out in color, print out the interferogram, whoa, at the same scale, like on letter paper, as you printed out the grid here, then you should be able to fold the interferogram along this line, or fold and lay it along the profile. They are exactly the same size. Now, not many people are going to have the capacity to do that, so I have a solution as an alternative. Okay. Benjamin is asking, could you expect to unmount this image with snafu, or is it too decorrelated? No, I think you could. You would want to make sure it didn't make any mistakes. Where am I going? Yeah, it's going to have some trouble in the areas where the fringe gradient is very large, but it looks continuous. I think it should be able to add up through there. But then it will get to somewhere around here and it will start to make stuff up. In the decorrelated areas, it will give you extremely high values of phase, and you just need to know that it's going to do that so you can mask them out. I think we'll see both tomorrow and on Wednesday that Snafu outputs what it calls a connected components mask, which is an estimate of what it thinks is continuous in the data. And that can often be a good way of removing things that are just noisy. Things that have zero connected components don't connect to anything, and decorrelated areas will certainly fit in there. But in general, this interferogram is unwrappable. You can see that actually you can also go around the outside and connect from one side of the interferogram to the other through here. So it should unwrap it all. Anyway, so yes, what I have concocted is, instead of having to print out the interferogram and print out the grid and lay one over the other, I have made a Google Draw document, which I showed you right here. Right, so if you click on that link, where am I going? Click on the link to the Google Draw document, it will take you here, where I have neatly aligned the grid with the interferogram and rotated the interferogram so that it aligns with the grid. You're all here. You cannot edit this document yourself. You will have to make a copy and then you can do whatever you want to it. I will not give you permission to edit this one because this one is mine, and it's mine for the purposes of these instructional workshops, and I will keep it as mine forever. But you can make a copy and edit your own. What you can see I've given you here is a series of dots, which of course if you click on them you can copy and paste them. Paste. You can make as many as you want. I've also given you a nice solid vertical line here, which you can then line up with where you think the first fringe crosses the profile line, about there maybe, and then you pick up your dot and place it on your profile somewhere in keeping with your interpretation of where you think the displacement is. Okay, so that's what I'm asking you to do. Put a series of dots on the plot to indicate displacement as you move along the profile. Remember that the ends of the profile are at 0. That will help a lot with trying to put everything in its proper place. And also I would recommend that once you get a certain distance along the profile line, you might start going in multiple fringes at a time. For example, 5 fringes is a nice round number of 14 centimeters of displacement. So you might want to start counting in 5s once you get to about the 5th fringe or something like that. Right, so I think I'm going to give you about 10 minutes to do this. And happy to answer questions as you go along. Yeah, and at the end, maybe we will look at some versions of the profiles, and I will also show you what I think the answer is. How's that sound? I'm sure it sounds great. Could I show you the link to where this Google Doc is? It's in the notebook. In the notebook, in the section of the notebook where we are talking about what we are doing here, which is essentially a phase unwrapping problem. We're trying to turn all of these fringes, which are, cyclical, repetitive, into a continuous profile of displacement. The link specifically is there. And there are other ways that you can do this too, of course. You can load it into any of these PDF editing programs. Yeah. And I even give you some hints, which you might want to read for yourself. If you are particularly advanced in this, there are a number of other questions that you can answer that follow here that maybe we can talk about as well. But first, I would like you to have a go at making a profile. This would be a good place to have some kind of light mood music or something to it. So I'm not sitting here in silence, but I don't know if you have such a thing, Melissa.
No, not right now. I could do the timer.
Yeah, maybe. Maybe about 8 minutes from here.
Okay.
It comes on. Maybe at that point, one of the early finishers will have the opportunity to show us what they have, how they have interpreted the profile. Well, okay. So I counted a 5 or 6 thumbs up. Would one of those people like to volunteer by putting their hand up to show us what they did? There are no extra bonus points for participation, but maybe the approbation of your peers and the thanks of the instructors for active participation would be very valuable. Okay, there's a hand up. Negin, you've taken this course before, so you should have it perfect. Do you want to share your screen and show us what you've got?
I can do that. Thank you. Can you see my screen?
I can.
Yeah, it's very rough estimation of what because of the points, but
Okay, so talk us through it.
so basically from this point, X from the left towards the middle, towards the fault basically, we actually observe the fringe, where the fringe starts, like as you mentioned, the change of the colors. And then we start counting them. And based on the counting of the location of that fringe, starting from the point, we estimate how much displacement it would be. So for instance, for this fringe, it's almost one fringe from the starting point. So I was thinking of it's about like almost 0.2, like 2 millimeters basically. And then going forward 2 centimeters, sorry, and then going down towards the center, it actually increases because the moving away from the satellite, so we have the subsidence. And then when it comes very close, sorry for my voice, it's very early morning in Australia, so, and when it comes down to the center close to the fault, we have the moving towards the satellite. Basically fringes is almost 2.5, so the uplift is happening at this point where we are getting closer to this side of the profile.
Okay.
So we see subsidence on the left side of the profile and also left side of the fault trace, and then uplift when we are going towards east.
Great. So one thing I might ask you about is the direction of the uplift. Now, I gave you a hint that you should start at 0 at both ends of the profile. If you did, what would happen to the uplift on the right-hand side?
So potentially uplift will be starting from somewhere here.
But I said maybe the end of the profile is 0.
Oh, I didn't pay attention to that.
Okay, but I think at least I can strongly agree with at least half of your profile.
Yeah, sure.
So thanks for showing that. And then maybe we'll get a second opinion.
Sure, thank you.
Thanks. So Stephen, would you like to show yours?
Yeah, good morning. Yep, I actually did. Yeah, the difference was, I just started from 0 from the other side, so it's kind of we have the same result, but I start from 0, so on the eastern part from X, and so the uplift is going towards the actual structure.
Yeah. Okay.
I grouped by 5, so I start from the first one, but then I start grouping the 5, so I then had to do it for all the put in dots for all the single fringes, and we get to sort of 60 centimeters on the hanging wall, and around probably 6 to almost 7 on the foot wall, so on the eastern side.
Okay, yeah, I like it. Maybe I'd fill in a bit more detail in the central part of that profile, just because I think you can.
Yeah, but it's just
Okay. Thanks. And Akshay also wants to show us, I guess.
Yeah, I can also show. So I'm not sure it's correct or not, but I have tried my best to add most of the interferograms over here, trying to use one like this, multiple ones. And on the left, starting with the 0, one over here with the last one, and this one, which was the half, and I'm not sure where it goes. I have taken this one as one of the interferograms, then this, and this.
Okay, so the one thing I think that some of the others show a little better is I think the gradient gets steeper in that central part where the fringes are very close together.
Yeah,
So
they're very
you have
close
it
together.
kind of
It's very.
you have it kind of linear. I would have it, I think, steepening
More
a little,
steep.
and then maybe even flattening out at the end. But But yeah, the bulk pattern is right. I think that the subsidence is happening on the left side and the uplift is happening on the right side, and it's quite asymmetric.
Yeah.
There's a lot more subsidence than there is uplift. Right, thanks for
Thank you.
showing. I'll show you mine, and then
Garrett, there is one question in the Q&A.
this might be why the uplift was not calculated from minus 0.56 meters and from 0. Why in the middle? Well, yes. Okay. Let me try and show my answer, and maybe that will help. Share screen. I've got to do that now. Where's my button? There. Screen share. All right. Let's see. So, if I click on this. All right. Here we are. So one thing I mentioned, that the far field is 0, and that's usually a good assumption for most places, right? So if you're far away from the fault, you see out here there are very few fringes, or there are none. Same possibly could be true over here, although it's decorrelated. Just take my word for it. And if you if you look at the whole interferogram, you can make it basically trace a path around the outside more or less from here to here, to assume that this is all 0. Okay, so that's one thing. And then in terms of the interpretation, okay, so I do the same thing you've all been doing. Start at 0 here. The first fringe crosses the line about there, so remember that's fringe 0.5, so that's about 1.4 centimeters. This would be 4.2 centimeters. One fringe further, I kind of eyeballed it, and kind of by my expert extrapolation figured out the fringe would cross at about here. The next one you can see is there. That's 2.5 fringes in. That's 7 centimeters. And after that, I went in 5s, like I kind of suggested, and I get something that looks a bit like that. Once you get to about here, you see that the fringes actually start curving round, and they might actually start to reverse, but there aren't actually any coherent fringes. But my suspicion would be that the pattern would actually enclose here, and you would start to go back up again. Okay, what about the other side? So, oh yeah, ignore everything that happens in here is decorrelated, so perhaps you don't want to start counting fringes through there. Instead, we'll start at the other end of the profile and count back in. Okay, so fault there, 0 here. Here I think is half a fringe. That's 1.4 centimeters of uplift. Here is the next fringe, about 4.2, and I think you're into the deep blue right here. Before if you went any further, you might have another red fringe there, but that would make me 7 centimeters of uplift. So my profile looks like this, with gradual and then steep subsidence, and then maybe at the bottom it might flatten out. If I was to put another marker in, it might actually. Yeah, if I was to put a marker in here, it might actually be going back up again. And then on this side, you're slowly but gradually uplifting towards the fault. Right, and the fault is a discontinuity. We know that the ground broke here, and we also know that the ground showed an offset of 25 to 30 centimeters, which is larger than the amount of subsidence that we measure. And it's probably because the profile would go back up again as you got closer to the fault. How do I count for decorrelated fringes? I told you, I eyeballed it. I tracked the trend along here, and then yeah, there's another one here, red to blue. Okay, I can see the blue. Maybe there's red there. Okay, there. That's how I did that. Yeah. You should all. Does everyone follow my reasoning here? I see a couple of questions, so maybe I should exit this and have a look. How do I account for decorrelated fringes? Okay, I answered that one. And then, if we are looking at 40 kilometers of distance, how strongly can atmospheric disturbances affect our 60 centimeters? It's difficult to say. Atmospheric disturbances are much easier to spot when you don't have much deformation. When the deformation field is flat and you have like real sort of weird blobs, then they're very obvious. In the case like this, where you can see lots of fringes, then they would just add a little extra deformation to what you're already seeing. But it wouldn't be true deformation. It would be the propagation delay of the signal through the troposphere. So it could add maybe or subtract 1 to 2 fringes of apparent displacement from your estimate, which in this case was probably about 10% maximum error. So we can, yeah, you should always be a little wary, I suppose, that there could be errors in your data. That's a good point to make. Let's see, I should go back to my notebook because there were a few more questions that I asked in there, and maybe we can use the group HiveMind to try and answer them. Am I here? No, I'm in the wrong. That's the wrong screen. Excuse me a second. I want this one. Yeah. Okay. Back to the notebook. So I asked, let's see, what's the total throw in the earthquake, which is the total uplift plus the total subsidence. There's the total relative vertical motion between the highest and lowest points. Anyone got an answer for that? It's going to depend a little bit on your estimate of what the subsidence was and how many fringes there were. Negan says 62, Mohammed 60. I think it's a little bit higher than that. Jeremy says 60 to 70, Sahel 70, 70, 65 to 70. Okay, I think we're in the right sort of ballpark here. My personal estimate was 66 centimeters, 21 fringes of subsidence and 2.5 of uplift. Okay, that's all in the right ballpark, I think. The ratio of uplift to subsidence, how many parts down per part up? Maybe express it as a ratio. 0.13, 14%. That's like 1 to 7, right? 7 down to 1 up. I think it's more like 8, maybe, or 8.5 to 1, something like that. But yes, those sorts of percentages are the right kinds of numbers, I think. And the final one, the final question, requires some trigonometry. Elastic modeling of the interferogram and information from seismology suggests that the fault dips at 40 degrees. Considering the throw observed, which is your number, your 65 to 70 centimeters, my 66 centimeters, how much slip on the fault would be required to produce it? Does anyone even have a clue about answering that? What would you need to do? It's a trigonometry question. If anyone has like a brilliant idea and comes up with a number, share it, and then in a second I will show you my reasoning. If there is no answer forthcoming. I'm sure everyone has their calculator at hand to do trig. I think I do have one here actually, buried in piles of stuff. Manuel says 99 centimeters, which is, I think, a pretty good estimate. 102, also a good estimate. And again, it's going to depend a little bit on what you think the throw is, which is your ability to count very, very closely spaced fringes at almost at the point where you don't have enough resolution to do that. Yeah, those are all good ballpark estimates. I will go back to like a full screen share, I think. Show my slides again. Yeah. All right. So yeah, my answers were basically very similar to yours. I estimated 21 fringes of subsidence, 2.5 of uplift, about 66 centimeters of throw. One point to make there is that this is the surface offset is smaller than that. My wording is all wrong here. The surface offset is smaller than the total throw, suggesting that maybe the fault slipped more at depth than at the surface. The surface offset is just the fault movement at the very surface, and it suggests that maybe deeper down the fault moved more. If you were then to use that estimate of the throw as the vertical offset associated with the fault movement, you want to measure the movement along the hypotenuse of this triangle, given 66 centimeters of vertical, right? And I told you that the dip of the fault was 40 degrees, so you can make some trigonometry, and the slip is the slip along the hypotenuse of the triangle is 66 centimeters divided by the sine of 40 degrees, which gives you something very close to 1 meter. And that's the number that several of you got. So well done, everyone. There's a couple of more things I wanted to show you. One is that I actually provided, if you want to go back and look at them, an overlay that you can put in Google Earth, and you can look at this area in a bit more detail. And you can look at your interferogram overlaid over the topography, and you'll see some agreement between what the things that you might expect to see. So, for example, the Dinar area, the city of Dinar is down here, all along the kind of the front of this range. So there's Dinar, and then there's this kind of valley that runs along the fault, which is along the front of this range. The very sort of sparsely spaced uplift fringes are all on that ridge, and all of the closely spaced subsiding fringes are all on the side of the mountain where there are lakes. So that kind of follows, I think. The ridge went up, the area where the lakes are went down. Also, if you look at the area where the lakes are decorrelated, which is not at all surprising. You would expect them to be. Water is not radar stable for the purposes of interferometry. Yeah, so you can learn a lot more about this if you took the geological example. This exercise comes out of a class I teach in active tectonics, where I'm trying to get people to think about faults and how they move. That's not necessarily everyone's interest here, but you can do things like you can try and calculate how many earthquakes it would take if it was just the uplift causing those mountains to form. How many earthquakes did it take to build those mountains? And if you had a recurrence interval of 1,000 years between earthquakes, how many thousands of years did it take to build the mountains, that kind of thing. Anyway, I'm not going to go into that today, but that's the sort of thing you can do here. And there are more details in the notebook if you want to go and read up on them. So I'll stop sharing that. I'll show you the denouement of the notebook just for fun. Where is that? Right here. Yeah. So if you really you're keen, you can go and read the paper written by Tim Wright. Eric Fielding was a co-author on that way back when. And Eric is on the call, so if he has any other insights he would like to provide, that would be great. The teaching exercise is part of an old UNAVCO, and the predecessor to EarthScope, an old UNAVCO teaching material set called GETSI. There's a link to that here too, so you can go and find those. And just to say, for the homework which is associated with this, please make a PDF of this completed notebook, and also a PDF or screen grab of your completed profile, and upload them to Moodle so that we can look at them. And hopefully you've internalized some of the advice that we have given you here in what to do with all that. Okay, so there's a couple more things to talk about. I mentioned one homework already. Earlier, Francisco mentioned the other one. I should probably have not unshared my screen, but I can reshare it, showing you the syllabus for today. Just to finish. So here we are. We are remarkably close to being on time. This is probably the first time this has ever happened. Very well done, everybody. My co-presenters for being timely. There are two things that you are being asked to do today to complete the exercises. The first one is to complete the modeling notebook from this morning that Francisco showed us. Complete the exercise. Do the grid search for the depth and the volume change. And once you have a series of answers, there is a quiz on Moodle where you basically can provide your answers. And if they are within an acceptable range, you will get it right. And if they are not, then maybe you should go back and try and model it again until you get something closer. The second thing is to submit your completed profile and your answers to the questions in the notebook. So all those things that we were just talking about, the throw and the faulting, there are spaces in the notebook for you to type your answers in. You might have to edit the cells to do that, but that's good practice. Make sure that those answers are reproduced in there, and then save your notebook as a PDF and upload it. Now, people have been having some issues with downloading, with saving their notebooks as PDFs. That should not happen here, because basically all I want to see is the text that you type in, and the text is always going to be saved fine in a PDF. Graphics, not always. We will work on that behind the scenes to see if there's a solution for that for some of the other notebooks to come. But yeah, all I would like to see is your completed profiles and your estimates of fault slip and throw and all that stuff. That is the homework for today. Lucas asked, when is the deadline for the homeworks? Well, we're going to let you have until the end of next week. So you're better off doing it today, because it's not very strenuous. I don't think either of those exercises are pretty straightforward to do, especially this one. But yes, do that as soon as possible. But yes, we will give everyone an extra week or so to complete the homeworks after the end of the course, because we do understand that some people are in incompatible time zones, or less compatible time zones, and it might be a kindness to give you a bit more time. But yeah, as soon as you can would be best. because you then won't forget, and we can build on what we've done today and the rest of the week. Anybody else got any questions? Because if not, we could even finish like a minute or two before like 4 hours are up. That would be nothing short of miraculous. Okay, everyone, thanks for coming. See you all tomorrow, where we will go into some processing, which is going to be awesome. The debut of like ICE 3 processing on the ICE Plus course.